Hello, hello. Daphne, hello.
Barry, you can start.
Okay, thank you. Hello, everyone. Mahaba, good morning, good afternoon, shalom, and welcome to our Satcom Vision virtual conference, which is funded by Profen and our gracious sponsors, Hughes Network Systems and Anuvu, all of whom will address you today. We are broadcasting from Profen Engineering in Ankara. My name is Barry Watson, your chairman for today, speaking to you from Blandford Forum in the UK. Our common subject for presentations is a 5-year reach roadmap vision of technological and market trends towards a Satcom renaissance downstream success. We've been waiting for a long time. Today's theme, ground station technologies for user terminals, GEO, LEO, and MEO. To help with this task, some of the hard work will be shouldered by our well-known moderator, Dr. Hector Fenech, a consultant now, but his last position prior to retirement was architect of Eutelsat's HTS, VHTS Connect program. Hector will introduce our program today and the presenters. But before Hector speaks, I would like to set the scene. Historically, let me commence with COVID-19 comments. Back in March, during our last virtual conference, great problems prevailed with the onset of a nasty third wave, whereupon we optimistically pronounced our future is not cancelled. This optimism was justified as many people now have the mitigating vaccination, implying that life can start near normal, which is what appears to be happening. Although, looking at this morning's news, not everyone is convinced. Now, the good news, despite COVID events of the past 18 months, our Satcom business progressed with challenges, slings and arrows of life, but relatively steadily with a number of notable milestones. The industry continues to transform Satcom towards a successful realization of downstream networks. To achieve this, I mentioned a determined and innovative bunch of employees and ever pressed by good visionary management. Our market shape. Just like Martin Luther King stated years ago, I have seen the light. Numerous profitable product. There is an epoch market opening, creating numerous profitable product opportunities when addressing fixed orbit, VHTS, HTS, GEO, plus the newly added geosynchronous LEO, MEO satellite constellations. However, one big innovative development to all potential customers tracking LEO satellites is the all singing, all dancing requirement for a comprehensive transmit receive, multi-orbit, multi-frequency, multi-beam antenna terminal, which shall be produced in quantity, cost effectively, and in operation seamlessly connect to these target satellites. Anyone achieving this over time will be deemed a winner. Predictably, there will be several successful candidates. As we read, many players, mostly venture capital funded, are engaged in innovative, novel, exciting development work, some stretching back over 5 years or more. However, to date, we have not seen many entrants with quantity product offerings satisfying appetites for consumer broadband, enterprise, or other potential markets quite yet. The overall task is not easy for any RF designer. It is equivalent to the term VD, very difficult, analogously in international mountain climbing terms. On the other hand, we're promised by all confident CEOs that cost-effective product FPAs will be available on a timely basis. To our audience, we shall hear a lot about these features from our presenters and learn more concerning reflector solutions, FPA solutions, and electronically scanned antenna solutions. Accordingly, there is financial reward for the user terminal suppliers, as the NSR consultancy states the flat plate antenna FPA market is predicted to generate circa 17 billion in total equipment revenue over the next 10 years. GeoHTS is to receive the largest cumulative equipment revenue of some 10 billion, whilst consumer broadband applications will unlock 1 billion for FPA manufacturers. So the marketplace is burgeoning. Well, folks, in many ways, we are only at the beginning of this story, even though I've been monitoring this for many years. We are now treading the low-level market foothills of user terminal suppliers in a very challenging, expectant, and demanding market. All terminals you will hear about today will enable seamless connection to any satellite in orbit and will be a game changer. Presenters, do your best to tell our audience and share your knowledge with them. Next, a small deviation before we commence our main agenda. I'd like to talk about the first commercial array antenna to enter a very early direct-to-home DTH marketplace in those halcyon days of the late 1980s. It is named the Spherical. It is a museum piece. Some may be familiar with the antenna type. It is a flat plate array. Now, everything needs a name, and the word Spherical is a portmanteau of the word square and the English word aerial, as the antenna used for receiving signals from the now defunct British Sky Broadcasting DTH service from B-Sky B. We are looking here at the development work, and this is, I'm going to show you over here. I can't see on the, I've got the main screen up here, so I can't see at the moment. With the development work, which started at ERA Technology in Leatherhead in the UK during the mid-80s. So it's almost, guys, almost 40 years ago. The Spherical is a true flat plate receive-only antenna configured in the form of a square, intended to be unobtrusive and possess a unique selling aperture shape. At this time, other competing commercial low EIRP satellites usually required a cumbersome 900mm aperture dish to receive clear signals from geo-transmitting satellites. The heavily advertised smaller antenna was emphasized as BSB's unique selling feature. Everyone in the marketplace at the time was surprised, including those companies signed to manufacture the receivers, which would have to work with the newfangled FPA. Probably 100,000 units sold eventually for use with the Marco Polo satellite until its demise in 1993. But gladly, that was not the end of the FPA story. Attractive, yes, it continued its working life as additional numbers were used to support the Scandinavian Tor satellite, French terrestrial relay satellites, and followed by Astra and Hotbird. Companies like Fortel and later Matsushita, now Panasonic, produced the Spherical in larger quantities. Finally, technically, for those who are interested, 2 versions were developed, using the first using waveguide technology with an array comprising 256 individual radiating elements fed by a distribution network, all realized on a copper-plated composite plastic structure. The second is a strip-line fed array, which I'm highlighting today. Both possessed aperture dimensions of 390 millimeters. In operation, the Spherical was configured to represent a diamond aperture to the target satellite to take advantage of the lower off-axis side lobes, increased isolation inherent in that plane to be aligned diagonally tip to tip with the geostationary arc or Clark belt. Now, I can't see, I'm not on the picture here, so I can't see. Definitely? Hello? Anyway, that's it. Here we go. I just got to get back. This is the Spherical. It looks pretty modern to me. I'm going to now take it apart and I'll take the cover plate off. Get there. Yeah. So this is the diamond shape, and that would be aligned in line with the geo arc. Inside, in this clamping area here is polystyrene, low loss dielectric. And then what we have, if I can show you this the best, like that. So here you have 256 radiating elements. So these are the radiators, strip line, and that's then fed in underneath this plate. There we are. Look, I can bring it up there, and that bit there. See, you see the blue marks underneath. That's the distribution network. So here it is, almost 40 years ago, and a wonderful piece of kit. And that was quite unique at the time. So I'll put this back. So I'll go on to the final part. So my contribution at that time, and I was just a youngish engineer, was to do the design work to introduce the novel diamond shape, because that was diamond antennas were all the rage at that time. So if you could look carefully when you are out and about in these regions, you may see a few remaining Spherical specimens fitted to walls of houses or within teleports. So at this juncture, what I'd like to do is to hand over to Hector, who will introduce our conference proceedings and presenters. Thanks.
Thank you, Barry. Good afternoon, good morning, or good evening, wherever you are. We have 10 or 11 presentations to go through, so I won't spend too much time, and I think we can move directly to the first presentation by Hakan Savasan from Profen, which is entitled Profen's Next Generation of Ka-band STOM Terminal. Hakan, you have the floor.
Thanks, Hector. I think you seeing my share screen and my voice is loud and clear. So let me start with a general overview of my company. Profen is a global group company established in 1995, and we are celebrating our 25th year. And we provide products and services in major markets such as satellite communication technologies, defense technologies, teleport and satellite network services, broadcast and media, EPC and life sciences as well. Our headquarters is in Istanbul, Turkey, and we have branch offices in Ankara, Turkey, Konya, Turkey, and Tewkesbury, United Kingdom. We provide solutions to our customers by combining different innovative technologies and disciplines including telecommunications infrastructures, satellite ground segment systems, data center design and installation, and defense technologies. We are an R&D-based company, almost allocating 20% of our yearly budget to our in-house research and development efforts to design and develop innovative solutions to our customers. Today, I will try to give you an overview of Profen's next generation Ka-band air SOTM terminal development initiative, which is a government-funded R&D project. Satellite communication on the move, SOTM technology, is the ability of a vehicle equipped with a satellite antenna to communicate with a satellite and maintain this communication while the vehicle is in motion. SOTM terminals can be used on land, sea, and air platforms to provide broadband satellite services for different purposes. For commercial airliners, there are two main use cases. The first one is the in-flight connectivity. The other one is the in-flight entertainment. There are basic design considerations for any SOTM terminal. First, you need to have a narrow beam to transmit broadband signals from satellite. You need to have a precise satellite tracking capability to maintain the communication, low side lobe levels, and low profile mechanical structure compliant with the strict aviation standards, small size and weight, low power consumption, high reliability, and a competitive price. Based on these design constraints, our main purpose is to design and develop a low profile, platform independent, and modem agnostic Ka-band SOTM terminal, which can be integrated into narrow and wide body commercial aircrafts to provide broadband data communication via satellite and compliant with environmental standards used in the aviation industry. You see the technical specifications of the terminal on the slide, and the parameters that I want to emphasize especially are the flat panel, the panel array antenna. It's an horn array. We had two different alternative designs for it, but we choose the horn array, which I will discuss in more detail in later slides. The weight is very important for us, so it's almost 36 kilograms, including all RX and TX electronic equipment. Hopefully, we will have a transmit EARP 49 dB watts and a tracking accuracy of less than 0.2 degrees RMS. The terminal is designed to be compatible with the following aviation equipment standards. The first one is the Orange 795 91. It's based on physical installation and aircraft interfaces standard. The 0160G, it is the environmental conditions and test procedures for airborne equipment standard, and the 0178B, it's the software part of the terminal. On the left-hand side, you see the concept of operations for an airborne SOTM. The SOTM VSAT is utilizing commercial Ku or Ka-band satellite transponders and can be called as aircraft earth station, that is providing functionality for transmission, reception, and processing of signals via satellite, given aeronautical and or broadband connectivity services in Ku or Ka bands. On the right-hand side, that figure shows the configuration and placement of our existing terminal elements. We are using an alternate Orange 795 compliant configuration layout without a Ku Ka-band RF unit in order to ensure platform independency. In this configuration, the HPA block up converter and block down converter is to be moved to outside antenna equipment inside the radome. And in this case, the HPA cooling becomes a critical item at that configuration. The most important aspect of the project of Profen is that this is the first flat panel antenna being designed and developed by us. From our point of view, the most critical stage is the creation of design alternatives for flat panel and the selection of the optimal one among in terms of technical performance, compatibility with standards, manufacturability, maintainability, and cost. We compared slotted arrays versus horn arrays with modeling and simulation studies and analysis, and we decided to use a horn array flat panel, which offers the most optimized results for us. You can see the front view of the combined panel structure of 1024 array. It's an array of 64 by 16 aperture antenna. After the diameter conversion of total surface area, the calculated aperture is 0.37 meters. Considering the entire antenna system, the antenna G over T ratio is expected to be over 13 dB over Kelvin based on power losses, atmospheric losses, cable and connector losses, and losses that will occur after the integration of the active products, defect structures, and other RMS errors that will affect the surface conductivity. In the figure, you can see the feed structure required for the use of both left-hand circular polarization and right-hand circular polarization. While we are designing the feed part, a distribution structure is preferred to preserve the symmetry in terms of phase and power. Since the structure should work in both circular polarizations, right-hand and left-hand, it is necessary to design two different polarization feed lines without interfering with each other. To collect the power in the feed structure, there must be a 180-degree phase difference at the E-plane T joints. For this reason, a 90-degree angle must be added to the E-plane to T joints. This is the first optimized structure of the SOTM antenna, and it is the feed antenna part where the radiation is. First, the long side of the feed antenna should be determined. Then simulation optimization studies should be done according to this figure. Since the antenna structure will operate in circular polarization, it is essential that the antenna opening is in the form of a circle or square. We choose a square geometry in the design to utilize the total surface efficiently. In square geometry, electromagnetic waves radiates in TE10 and TE01 modes. Analysis of these modes should include the lowest frequency of the receive band and the highest frequency of the transmit band. After optimizing the cutoff frequencies of the antenna, optimization studies of septum structure, which provides circular polarization, were carried out. For the structure to work well in both bands, it is designed based on the Gaussian distribution of two different wavelengths to be parallel to the septum structure. In addition, it is important to accurately determine the septum thickness of the polarizer structure, which enables the antenna to operate in circular polarization. The mechanical and dimensions of feeding antenna are shown on the slide. I will show you some figures related with our initial simulations and studies. This is the simulated RX gain pattern in the figure. The 1024 aperture array antenna gain is approximately 36.64 dB in the receive band. Asymmetrical radiation is prevented by providing 10.15 millimeter distance between the centers of the antenna's small elements. This is the simulated TX gain pattern in figure, which is 40.51 dB. Although the wavelength is smaller, no side beams observed, which validates our theoretical studies. And this is the antenna exit ratio at receive frequency as 1.71. Terminal will have an azimuth elevation aperture positioner with an elevation coverage of 0 to 90 degrees and azimuth coverage of 0 to 360 degrees continuous. The use of two-axial antenna motion systems on fixed or moving systems requires different modeling techniques. Moving antenna systems have a more complex control algorithm due to change in position relative to Earth's surface. Angular velocity of the moving platform is used to stabilize a line of sight in mobile systems. Sensors where angular velocity are streamed usually have low measurement errors for short periods of time, but error rates increase in long-term use. For that reason, line of sight stabilization in mobile antenna systems is not a sufficient approach on its own. With the stabilization of the line of sight, tracking algorithms should also be integrated into the system to keep the RF signal level at maximum. Before designing the control algorithm of the mobile azimuth elevation antenna system, the forward and inverse kinematic models of the system should be drawn. In this context, the antenna system can be examined as a two-axis robotic system in kinematic analysis. These are the animations for azimuth and elevation movements. These are our initial studies. Of course, there are many challenges in the design, development, and productization stages of this type of a product. Our top three challenges are product qualification, identifying cost-effective production processes, and platform integration. To carry out the product qualification process smoothly and not to face with major design changes later, we are conducting all system engineering activities, starting from system requirements based on DO160G and DO168B standards. Since the end product shall be competitive with the similar ones in the market in terms of cost as well as technical performance, we have to focus on cost-effective production processes for serial production. We are considering different techniques, including production with machining and additive manufacturing. Product integration is another very important challenge for us, since we are aiming at platform-independent mechanical structure. All design activities are based on Orange 791 standard to provide an easy-to-integrate solution for narrow and wide-body aircrafts. This is our roadmap for the products. We are planning in early 2022 within the Q1 to fix the design and start an iterative process for prototype production, which we plan to have a fully working DO160 ready technology readiness level 7 prototype in Q1 of 2023, and we are planning to finalize productization qualification in 2024, hopefully in half one. As conclusions, we completed preliminary design and now working on critical design. We are planning final design to be fixed in 2022 Q1. We considered two alternative designs for flat panel structure, horn array versus slotted array. We choose horn array structure mainly due to bandwidth of Ka band, Rx and Tx frequencies. The product will have an azimuth elevation movement system and will be modem and platform agnostic, compliant with Orange 791 standard. We are still evaluating the production process, machining versus 3D printing. There are pros and cons to be considered, but 3D printing seems very promising with the existing maturity level of the additive manufacturing. First working prototype will be ready in 2022 Q3. First DO160 qualification ready product is expected to be in 2023 Q3. Thanks for your attention, and this concludes my presentation.
Thank you, Hakan. If there are questions, please use the Q&A section at the bottom of your screen. I have a question to get the ball rolling. Since this antenna protrudes on the outside of aircraft, I presume there must be some requirements to limit the aerodynamic drag. How is this specified?
In fact, we are planning, our design is based on to be used with the fuselage radomes, the existing fuselage radomes. So at that case, the drag coefficient and the drag effect becomes irrelevant for our existing design. So we are planning to install it with the qualified radomes, but we have a very small dimension which are compatible with the fuselage mount radomes, and it's around 98 centimeter versus 32 centimeter.
Thank
So
you.
we have a very we will have a very low profile antenna.
Okay, thanks very much, Hakan. I see that there are no questions at the stage, so we can move to the next presenter. That would be Kartik. The presentation is entitled Multi-Transport Solutions, GEO, MEO, LEO, and LTE 5G. And Kartik is from HNS. Kartik, you've got the floor.
Hi, Hector. How are you doing? Hakan, if you can stop presenting, I can start presenting, sharing my screen.
Okay, go ahead.
I already stopped sharing, but
There we go.
Good.
Thank you very much. All right, Hector, can you see my screen?
Yes,
Great.
we can.
Perfect. Thank you. Hi, once again, my name is Kartik Seshadri. I'm with Hughes, and we are the satellite communication, broadband communication service provider behind HughesNet, with over 1.5 million subscribers in the United States, Americas, Mexico. We work and we provide our ground segment systems to enable satellite-based internet to various service partners and providers around the world. My main focus and my main job is to run a global service delivery business where we work with our international strategic customers to enable HughesNet services across the globe. So we work with different ISPs across the world in different countries to ensure that they get the maximum bang for the buck, maximum bits per second out of our baseband system. So I'm really excited to be talking about multi-transport solutions and technologies today, including GEO satellites, using MEO satellites, low Earth orbit satellites, as well as LTE, 4G, 5G technologies. I don't believe there's ever a ISP person that you would talk to, someone who has to deliver service, who thinks that he always has enough bandwidth. And especially with the pandemic over the last 1.5 years, connectivity is essential, as essential as electricity, and for school, work, finances. And I think all ISPs saw a huge uptake in the amount of bandwidth being used per subscriber. So when we started hearing about LEOs and MEO constellations coming up, it's actually music to our ears from someone who provides services mainly on GEO high throughput satellites, because this means that there's more bandwidth. And as I said before, there's never enough bandwidth, and they're not adversarial. I think it's complementary, and both can work together. And so we are looking at, I'm very excited looking at a future where we believe there's going to be, has to be multi-orbit solutions where we leverage the best of GEO, which can focus a lot of capacity into a single area in a very cost-efficient manner, versus LEOs and MEOs who also deliver capacity, but at lower latencies, but not quite as cost effectively. So if you marry the two together using various ground segment technologies, as well as what we're going to hear about from my distinguished colleagues in this panel, when they talk about multi-frequency, multi-satellite, multi-beam antennas, those are all very key enablers for multi-orbit solutions to take place. So we look forward to integrating all these antennas and solutions with our products to deliver a seamless service to our customers, and in a very cost-efficient manner. At the end of the day, if it's not cost-efficient, it's not going to work. The other thing that we're also, also believe in is multi-service network. So whatever baseband technology, like for example, our Jupiter technology has to be multi-service in the sense that it should we cannot have a dedicated network for consumer broadband and another network for mobility, aero mobility, and other applications, enterprise applications. A single baseband system or ground segment technology, if you will, that will address all these verticals would make it more efficient and cost effective, and optimize the overall capacity that's available. And the third most important tenet is really the multi-transport piece. And I'm not talking just about GEO and LEO and MEO, but also 4G, 5G, whatever's coming in. How can we leverage the best of every one of these transports to better suit our customers and provide better service more cost effectively, especially since there's so much more traffic now per subscriber. And for us, the key from a ground segment perspective, what Hughes has been working on for a while now is really the active technologies, which is we call our SD-WAN solution, if you will. The idea behind our active technologies is that it will allow for a more consistent user experience, irrespective of the kind of traffic that's running behind a VSAT, a modem. The SD-WAN technologies that we've brought to market in our active technologies is can handle high latency networks, packet loss, typical broadband network challenges where you don't have dedicated links, where you're running on a broadband network, and makes the best out of it, and you can run voice and other high QoS sessions. So active technologies from Hughes in our modems is really the key enabler here. So in a nutshell, active technology is a piece of software that runs on our modems, and what it enables is high QoS services on what is predominantly a broadband network. So it makes up. So one of the things that we do is we have a patented mechanism to measure the actual capacity available real time in every link that a site is connected to, and then dynamically classifies the traffic based on the type of traffic, with streaming, bulk, email, VPN, etc. And it's able to classify it very optimally so as to give the best possible SLAs for that session. So as we trend the capacity, we also manage prioritization within that capacity in order to give the best of performance to the end users. And it's agnostic to transport, and that's the beauty of it, is that it's not just a VSAT specific function. If I have a cable network, a fiber network, an Ethernet, an LTE 4G, a LEO, a MEO, it would adapt to every one of those transports, measure every one of them, and allow us to use the best of all the worlds possible. In terms of, if you have a diverse connection at a location, it will automatically decide which path is best for what application. So there are low latency applications, very collaborative applications like Zoom and Teams. It would use the appropriate access technology. On the other hand, streaming, heavy download volume applications might get pushed to something like a geo satellite, a HTS satellite, where you have a lot more quota. And it will control things like capacity, packet loss, jitter, latency. So this ensures a very high quality of service to the end customer. So this active technologies is what's enabling us to provide very high SLA services to all our customers. In fact, we have over 40,000 to 50,000 SD-WAN active technologies customers in the US alone. And one quick thing is, this wasn't developed overnight. This is some software that we've been working on since inception of initial SPEP spoofing and some of our modems. We started venturing into handling compression, understanding broadband QoS. We added dynamic traffic classification. Then we started supporting multipath technologies, metering it. That's really important, because if I'm going to be using a 4G or a 5G alternate network, if I use a geo satellite and a 4G together, I need to be able to meter it. And then of course, the ability to provide web QoE analytics, multipath VSAT, if it's geo, LEO, and others. So this is actually in action today. We have a product called the HT2100L. So I thought I'd just talk about a very quick use case where we actually have a Hughes modem that does both VSAT and LTE. We're calling it Fusion. And what it allows us to do is it allows us to route packets and sessions across both paths using active technology. So we're able to take a packet, send a request over the LTE link. The VSAT has both LTE and high throughput satellite GEO. It's talking to our Jupiter satellite GEO, and it can work with any satellite. But the bottom line is I can send very quick requests, very small packets over the LTE, which might be a smaller metered connection, and get a large response over the high throughput satellite GEO, which has a lot more capacity and a lot more quota. And for applications that are very, very latency sensitive, be it gaming or maybe some specific SAP-based applications, that will automatically get classified and routed over the lower latency LTE link. And also we look to minimize the LTE usage and enhance downloads over the satellite. This ensures that you're not overrunning and you can provide it in a more cost-effective manner. So the SD-WAN based active technologies allows us to provide a very high availability, as I said, because we're getting the best of both worlds. If one of the links were to fail or have a brownout, we can easily switch all the traffic over to the active link. And at the end of the day, it provides a lower cost to the end user. So whether it's an enterprise or a consumer, we're able to provide them a really high quality of service at a very comparatively much cheaper price. So we're very excited about our HT2100L, and we're going to bring it to the global market end of the year, beginning next year, Q1 as well. And we think, and then we'll have further optimizations on top of that. And if you just take another step forward as to where this is going, okay, GEO VSAT with LTE, that's great. Now we have LEO constellations up there where guys like OneWeb, who we are partnering with in certain countries, as well as we have our own GEO services. So why not apply the same concept to a LEO GEO hybrid solution, if you will? So think about this use case where you have both a LEO and a GEO at an enterprise bank or a bank branch or any enterprise location where they get the best of both worlds. They use LEOs for the more interactive Zoom, video conferencing collaboration experience, and then traffic gets shifted over to GEO for consumer internet, guest services, guest broadband, streaming, and other applications. And all this can be enabled, right from the same modem. Obviously, the challenge here is really the cost of the terminal. For the LEO, the GEO costs are pretty low for the terminal, but the LEO cost of the antenna with the modem and the integration. So we look forward to a very exciting future now, especially over the next year or two, where a lot of new players in the market are going to bring to bear, hopefully cheaper, more capable, smaller form factor antennas that we can integrate with and meet our future bandwidth requirements, which are just growing exponentially. With that, Hector, any questions? Hector, you're on mute.
Thank you, Karthik, and thank you for pointing out that I was muted. I don't see any questions on the Q&A. I'd like to encourage the audience to put questions. This is the moment that you can ask whatever questions you'd like to the presenters. In the meantime, I think I can ask a question myself. On the last slide, you shown a system, a hybrid system with LEO and GEO. And basically, the traffic would be routed as appropriate. If you need latency, it would go via LEO. If you need volume, it might go via GEO, etc., etc. How far away is it in technology-wise?
So technology-wise, it's possible. And we actually demonstrated this during the satellite show in Washington, D.C., pretty close to where I live, where we actually did the OneWeb LEO satellite, where we demonstrated it during the show for some press folks. One small nuance, but an important nuance to what you said was we actually a single session, we can actually make the request over LEO and get the response over GEO. So it's not just sending one application one way and the other application the other way. We actually, the flows can be mixed over both LEO and GEO. So it's a very capable, very smart way of running a network. So, but yeah, this is here. It's there today. Technically, it's here today. How it's going to pan out practically at the customer locations, and what the cost is going to be, and how it's going to be priced, and what all would be required logistically to make it work. The integration, that's the challenge, and that will be dictated by our customer requirements. And but technologically, the solution is there today.
Thank you, Karthik. I think we can move to the next presenter, and that would be Doug from Freefall Aerospace. And the presentation is called Kirkalex, the all-sky antenna. Doug, you've got the floor.
Okay, thank you very much, Hector. Thanks everybody for joining and the opportunity to speak to you today. My name is Doug Stetson. I'm the president of Freefall Aerospace. We're a small company located in Tucson, Arizona. And today I'm actually also representing Mr. Thomas Choi of Curvilux. Tom was not able to be here today, but our two companies, Curvilux and Freefall, have started working very closely together on a number of interesting antenna applications, both for ground, space, as well as terrestrial wireless. I want to share one particular new concept with you today. We call our all-sky antenna. This is something that we've been working on at Freefall for a while, and I think has a lot of interesting features for the challenges that Barry mentioned at the very beginning of the conference. A little bit about the company. Freefall Aerospace is a spin-off company from the University of Arizona, located here in Tucson. My co-founder is a professor of radio astronomy at the University of Arizona. And the bulk of our technology is really based on research in high-frequency radio astronomy. And I'm sure you won't be surprised that there are a lot of commonalities between the challenges of high-frequency radio astronomy and the types of challenges that Barry mentioned in tracking and communicating with the various constellations of orbiting satellites that are coming online now. So we think this gives us a really kind of a unique perspective on some of these challenges and technologies that are going to be required for the future. And one of those in particular is what we refer to as our all-sky antenna. So one particular implementation of this is really derived from the Erecibo Radio Observatory. And as everyone probably knows, that unfortunately met its demise down in Puerto Rico last year. But Erecibo was built in the 1960s as a spherical reflecting dish. And you can see it's embedded into the ground, built in a depression in the earth in Puerto Rico, a very large reflector, 300 meters or so in diameter. And spherical reflector has a lot of very interesting advantages, especially now for the challenges of communicating with and tracking the orbiting constellations. A spherical reflecting surface has a very wide field of view. Can see essentially the entire sky above it. That's why we call ours the all-sky antenna. And the way the beam is steered in the case of Erecibo was by using in that case, very large waveguide feed structure that was suspended above the dish by a series of tracks and pulleys, very complicated mechanisms. And that was working down in the 200 megahertz range. So the structures were quite large. What we have done is take that basic paradigm and miniaturized it extensively down to a form factor that's compatible with small user terminals as well as larger teleport ground stations. but follows the same basic paradigm of a spherical reflecting surface, which remains stationary. So we have no need to physically turn the dish itself. What we do is move the small feed system that's located in the center of the reflector dish, and that allows us to steer the beam through very wide angles in azimuth and elevation very rapidly, and again, without any physical movement of the reflector dish itself. So this can be done in a very lightweight, low power, low profile form. You can kind of see a little bit here. There's an animation going on the right there. The basic concept is pretty straightforward. Once again, we are steering the beam by moving the very lightweight feed system, which can be moved very rapidly and very accurately. By leaving the reflector itself stationary, you can imagine the tremendous reduction in infrastructure, mass, and power that's required to enable the beam steering. So compared to the traditional old school steerable parabolic dish antenna, we eliminate much of the physical structure, the mounts and motors that are required to turn the parabolic dish. So there's a significant reduction in overall structure and cost from that perspective. And compared to the the flat panel phase array technology, which is becoming very common now, we don't use any phase shifters. We don't have multiple radiating antenna elements. So there's a great reduction in overall power and cost required compared to the flat panel ESAs and phased arrays, phase array systems. Because of the features of the spherical reflector, a sphere is symmetric about all axes. It has essentially an infinite number of axes of symmetry, compared to a parabola, which only has one axis of symmetry. So that allows us, as we steer the feed system, to always keep it on axis. And therefore, we can steer the beam through very wide angles with essentially no drop in gain. Now, of course, as we get to the very edge of the reflector dish, we'll see spillover, growth in side lobes. And so there are some limitations in this particular configuration in the amount of elevation steering that's possible. But basically that we can steer through 360 degrees in azimuth and from zenith to near the horizon, 10 to 15 degrees above the horizon before the beam begins to degrade due to dish spillover. The feed system itself is very lightweight. We have elevation and azimuth motors that allow us to steer the beam very rapidly. So we can do very rapid retrace to pick up, to transform from a setting satellite to a rising satellite, and totally flexible to communicate with various orbit constellations. And the feed system itself, of course, is we have a number of designs of this. It's dual polarization, right-hand, left-hand, circular. It can also do linear polarization if that's required. So that's the basic concept. Right now, we are building our first prototype. Right now, it is a Ka band system, shown there on the left with the radome on top. In this particular case, we're using a approximately 88 centimeter spherical reflector, which is incorporated inside the radome. And once again, the reflector itself remains stationary. We move the feed system to acquire and track satellites. This is Ka band, but the technology can be used at virtually any frequency. We've actually built systems or modeled and simulated systems from L band all the way up through Ka band, and in fact, even higher than that. So it's quite flexible technology. Of course, everything scales by wavelength size. So we're very excited about this. We think it's essentially the ideal compromise or sweet spot between the simple parabolic dish antennas and the more complex but very flexible steerable flat panel phase arrays, and has the potential to enable the lowest cost, steerable communication for the variety of constellations that are coming online. It's very low profile because it does not require the vertical structure gimbal mounts that a typical parabolic dish antenna would require. The reflector itself is stationary, reduces power, reduces mass, can provide very rapid autonomous satellite acquisition and tracking, and compatible with the variety of constellations that are coming online. So we see a lot of applications throughout enterprise and commercial government, as well as even consumer applications for this type of technology. I did also want to mention that this can be even used at very large, much larger sizes. We're studying right now 2.4 up to even 5 meter systems, and this can mimic very much more closely the original design of the Erecibo radio telescope. Can even be embedded into the ground, since the dish itself does not need to move and does not need the gimbal mounts and vertical structure that a typical large antenna would require. So for the antenna farms, teleports that are being that are common today, this can have a lot of advantages. Very low profile, can provide aerial efficiency in terms of aperture per unit area. We calculate that can be increased by from 2 up to 3.5 times because the dishes can be spaced much more closely together, out of the wind and other environmental effects, and much more acceptable in rural and urban locations because they won't have the visual clutter that many of the large antenna farms will cause, and so there won't be as much a community resistance to that type of an approach. Before I close, I did want to share with you that we're using the same basic technology in space as on the ground. This is actually where we started at Freefall Aerospace, using in this case, an inflatable spherical reflector. Has many of the same attributes that I just described to you, advantages of the spherical reflector. We have developed an inflatable system which can be packaged inside a small spacecraft, a 6U CubeSat, for example, that you see there. This provides an extremely lightweight but large aperture, and therefore high gain antenna that can be deployed on orbit. We're actually launching this. The first spaceflight validation will be this coming June on a project we call CatSat for the University of Arizona Wildcats. This will validate the concept for packaging, inflation, and deployment of the system at X-band. And of course, this can be developed at KU, Ka band as well. We're working on those right now. So after that spaceflight validation, this will be essentially ready for prime time. Curvilux also has a program they call CurvaNet, which is moving towards initial operations, hopefully in 2023. We'll use some of our same technology, spherical reflector, in this case for a multi-beam capability, really focusing on enabling remote and rural connectivity that's so important to all of us today. So that's the summary of the technologies. Our two companies are working closely together on what we consider a science-driven approach to these new connectivity solutions. Between us, we have a very experienced and innovative R&D team looking at markets across the globe, in space, on the ground, and for terrestrial wireless as well. And all of us together, of course, it's a common theme, striving to make low-cost global connectivity a reality. So it's a very exciting time. Thank you very much for your attention. Be glad to answer any questions. And thanks again.
Thanks, Doug. You actually have a question from the audience. And the question is, how fast is beam pointing from a setting satellite to a rising satellite?
Yeah, that's an excellent question. We're working on that right now. Of course, everything's a trade-off between the cost and the size of the motors that we use. Currently, we are in our prototype design, we can move the feed system at approximately 180 degrees per second. And that allows us to do a complete reset from setting to a rising satellite in less than a third of a second. It'll depend a lot, of course, on the particulars of the orbit constellation. If we don't, and typically, you know, for tracking multi-satellites within a single orbit constellation, there wouldn't be the need to move through the full range of azimuth and elevation. So it could be much faster than that, but 180 degrees per second is kind of our target right now. The motors that we are incorporating in our prototypes will allow that. And so we think that is one of the attributes of this type of a system that's going to be very attractive.
As a supplementary question, I'll ask what are the effects of the pillars as the feed passes between them?
Yeah.
Is there any shadowing or?
Yeah, that's an excellent question. Actually, we're working on that right now. The answer is yes. You could see, obviously, there's some internal structure. There are some effects on side lobes, especially. And somewhat surprisingly, it's not, they're really not dramatic. We have developed we're using absorbing coatings, RF absorbing coatings on the internal structure, which mitigate that to a large degree. We're also looking at a few modifications of the supports compared to what you saw in the graphics to help minimize that. But that is something that we're working on right now. There's virtually no impact on the gain of the antenna itself. There is some growth in side lobes as we steer to certain angles. And again, we're mitigating that using RF absorbing coatings and maybe some slight modification of the structure. That's an excellent question.
You have another question, and we'll stop there so that we can progress. Do you envisage a multi-beam solution?
Well, yes, I do. The concept that I showed you here is a single beam. We have a number of opportunities. We can actually mount multiple feeds on the arm. So there is a possibility to, within the system that I showed you, to incorporate multi-beams. We have a different implementation we're working on with Curvilux that has multiple feeds inside. It has a somewhat different steering mechanism. And so the answer is yes. We're working right now on a multi-beam solution that's somewhat farther downstream. So hopefully the prototype that I showed you is being developed now and should be ready for actually distribution later this next year. The multi-beam antenna will be a little bit farther along, but yeah, we're working on both of those.
Thank you, Doc.
Thank you.
We'll move to the next presenter, Rush from Kymeta. And the presentation is entitled Next Generation Antennas for Real-World Mobility.
Hello, Hector. Can you hear me?
Yes, I can.
Okay.
I can see the presentation as well.
Okay, fantastic. Well, thank you for the invitation to everyone, and very nice to meet the industry colleagues virtually. So I'm working for Kymeta, and so I'm going to give you a quick rundown of the current solutions with Kymeta, and also our roadmap that's coming through and some of the testing we're doing at the moment. So, you know, I think we all are fully familiar with the situation. Connectivity is required ubiquitously. It needs to be connected everywhere. These are just some of the applications that we are focusing on. Our antenna, initially the U7 and now the U8 antenna that we launched last year, has really focused on areas of the land and maritime. We don't have an aviation solution today, so our focus area has been aimed to provide connectivity to first responders, military, rail networks, and vehicular solutions around the world. But the solution that can be provided by satellite only needs to be complemented, we believe, by a mobile broadband solution. And so we can see from here that there are many areas of the world that may have mobile connectivity or cellular connectivity, but they're centered around very dense areas. And as a result of that, we get many drop calls. We have unpredictable QoS, which is not easy to do on a cellular network. And so we believe, and that's why we designed the U8, to combine both an SD-WAN solution, as we saw from Karthik earlier, and integrating it into our U8 to combine with GEO satellite initially, and then longer term with LEO satellite. So how does the industry look today, or how does the space industry look? I think there's been some phenomenal evolution in multiple areas of the industry today. On the left-hand side, space and satellites is definitely the most exciting. In the old days, we had GEO KU, we had HTS, we have LEO and LEO VHTS. And on the space side, we can see that the number of satellites is going to grow from 5,000 to 25,000 over the next 5 years. On user terminals, where we fit in, we are a flat panel electronically steered antenna, and our focus area has been to drive the cost down and produce a affordable antenna for the enterprise initially, and then obviously working towards the future, towards consumer broadband. And you know, customers demand an always connected solution, so we combine both the cellular connectivity, LTE 5G, with the satellite connectivity with the GEO, and in the future NGSO. On the manufacturing, these are just some of our partners. Airbus works with us. Obviously, manufacturing has advanced dramatically. The need to build very low-cost satellites, nano satellites, and also LEO satellites has driven the price down. And combined with that, we have Blue Origin, SpaceX, and other launchers that are driving the cost of the launch programs down, which is fantastic. And then we have obviously multi-orbit solutions on the left-hand side. What we can see here is in the next 10 years, there's just going to be continuous evolution and continuous innovation in this industry, wherever you are, whether it's the user terminal, space, manufacturing, or launch capability. So we believe within Kymeta that we are one of the solutions to unlock the billions invested in next-gen satellites. So, you know, you can see on the top part of this slide, all the different, and these are only some of the major constellations. I think there's many more out there, but these are some of the large global constellations that are already been announced and being built and going live. Below that, we are also defining some of the cellular global operators that we believe that will start to play a major part in combining Satcom and cellular solutions. And then we fit at the bottom on the ground systems, ground antennas. And our area has been to really focus on the best of breed solution to combine these technologies into one physical unit. And these are just some of the verticals that we already have, around 1,000 terminals deployed across the world in all markets, providing these type of solutions. So you can see on the left, on the right-hand side, some of the real-world applications again there, which we spoke about. This is a connectivity on a bus, initially to provide telemetry, but also providing internet passenger connectivity, rail networks, both passenger and cargo rail networks, and then our traditional vehicular solution that is used commonly around the world. But true comms on the move, SOTM, requires agile beam steering, and that's very, very important. We have an algorithm that's we've been optimizing over the years to switch between satellites and between cellular and satellite. The ability to recover from blockages as you go under tunnels, that's really important for buffering. Compatibility with the LEO networks via software-defined, you know, that's an area that we are spending a lot of time on in our software area, ensuring that software-defined capabilities allow the switchover between the GEO and the future LEO. And low power consumption, somebody said it before, I think that's a really important thing, that some of our comparisons to the phased array larger antennas is our low power consumption, which allows it to go into cars and other power limited solutions. And what we do is build upon that and leverage the experience with the GEO terminals. You know, we're starting and have started on GEO KU band, and we'll have a KA band antenna in a few years' time. And there's advances in component miniaturization to drive the cost down and increase the capabilities. So what does the U8 antenna look like? It's low profile, it's about 14 centimeters in height. It's lightweight, it's around 23 kg. It's low power consumption. Average power consumption is about 35 watts with a peak draw around 250 watts. It's industry leading pointing algorithm to switch between satellites and cellular. The full duplex, the transmit and the receive is on a single aperture. It's software defined. Low maintenance is an important thing. one of the differences between us and a mechanically steered antenna is its pure software, therefore hopefully making it easier to maintain and to support in the ground. It supports various Satcom modems, so as long as the modem supports Open AMIP, we have it compatible with the U8. We have two versions of the U8. One is allows an external modem to be combined, and one has an internal modem. And those internal modems today are the IQ200 and the 950MP for the military. And we are LEO capable. What that means is, and I'll show you in a second, is that we have tested on LEOs, and these U8s that have been deployed will be upgradable to support LEOs. So what does the Kymeta U8 technology incorporate? It's metamaterial equipment that's been built. Without going through all the different components, I've tried to highlight all the key things. The key things here, that there's no mechanical parts. So on the left-hand side, we've been through this. The transmit receive is via a single aperture. It's wide-angle scanning to provide excellent beam performance. It is electronically controlled pointing, low power consumption, we spoke about that, and it leverages existing flat panel production techniques such as LCD to drive the cost down. We already have optimized the cost of the antenna, but we continue over the next 2 years to drive that cost down even further into hopefully single digits. The U8 specifications, without running through each point, I think the key things here are that it's a KU band antenna. It's about 82 centimeter in active diameter. The transmit receive frequencies are there, and the G/T on the broadside and the TX gain. The weight, as I said, it's very light. We also have a flyaway solution called the U8 Go. The power consumption is very low power, to about 35 watts. And one of the key things that we learned from the U7 is the ability to go into very difficult terrains with high temperature, so +70 with solar loading and -40, especially in some of our maritime solutions, which are going into colder areas of the world. One of the key things that our customers wanted is something that's easy to install. Not every time you have a solutions engineer or an installation engineer that's available. So we wanted to build an antenna that was very easy to install, very quick to deploy, very quick to acquire into the satellites. And this is really shown on the left-hand side, easily mounted onto a Humvee on a military solution. And on the right-hand side, that video can be downloaded from YouTube, shows it operating in the US at 100 knots without losing lock. And we currently, we provided a solution there, a demonstration at CES Space 2021. So moving on to the LEOs, we have done a demo last year, the GEO-LEO demo with Kepler Communications. This was a single U8 antenna. So we were connecting to 8 different satellites, 6 LEO and 2 GEO on 2 different GEO teleports. The GEO tracking was done with 2 different modems. One was an iDirect 950MP satellite modem in linear polarization, and the LEO tracking was done with a Comtech CDM 6760. The reason the Comtech was used is Kepler are building their own LEO compatible modem, which wasn't available at the time. They have made it available now. What we demonstrated was the ability to switch between GEO and LEO in real time without losing any communications. Just very quickly, this is just a quick, hopefully you can see this, a quick video showing what we did with OneWeb.
Rush, while we're watching, can I ask a question?
Sure, I was going. Yeah. Yeah. Sorry. Yeah, and that's the last slide. Just if you don't mind, Hector, I'll just finish it off quickly, just to show very quickly the roadmap. So we're obviously focusing now on our 2022 upgradable to upgrade the UH to the LEO compatible. There's some additional upgrade packs that will come with that. In 2023, we'll launch our first KA band solution. In 2024, a small factor LEO solution, and in 2025, which was the initial incarnation of Kymeta to provide the connected vehicle solution. So absolutely, sorry to interrupt. I'm happy to answer any questions now.
My apologies, Rash. I wasn't trying to interrupt. I was trying to
No,
be
it's fine. No problem. No problem.
You make reference that the aperture is transmit receive.
Yeah.
How do you handle the frequency difference for transmit receive? Typically, you have 50% difference. The one frequency is 1.5 times the other. So how do you manage the fact that you're dealing with frequencies that are so different?
So I'll get an answer from our technical solution engineer on that one. I won't answer that today because that's I don't want to give you the wrong answer. That's all. I'll give.
No, that's fine.
Yeah.
I don't think I'll see any further questions from the audience. So okay. I'll ask another question then.
No problem.
You've mentioned operation with LEO. So yep. That means you need to be able to have two beams, one for the incoming satellite, so to speak, and one for the outgoing satellite. How do you do that?
So we're in the early stages, as we did the testing on a static test switching between the GEO and the LEO with OneWeb and with Kepler. At this present time, we're working with the different LEO providers to define whether we're going to do a make before break or break before make solution. We haven't defined that exactly, so that's at the early stages at this time. So in theory, both solutions will be required to switch between the two multi-orbit solutions. But we have tested it theoretically in the labs. It's now early next year, we'll be testing it live in the real world scenario.
And we have another question. Will a multi-beam version have a larger aperture?
At the no. So the U8, the U8 KU, which is the current incarnation, will have this. It is going to be LEO upgradable. So we'll have an upgrade pack that will be allowed to switch over between the existing aperture. In other words, you use the same aperture that you've got out today and just change the baseband equipment, so the modem and the LMB and buck. We will also have a new U8 LEO coming out later next year, but also a KA band, which will have a different aperture. So the KU one today is the same. The KA one, yes, it's in current design and may be different.
Thank you very much, Rash.
No problem.
We move to the next presenter, Russell, from Hanoi Phaser, and the presentation is entitled Interoperable with Any Orbit, No Compromise on Performance. Russ, you have the floor.
Thank you, sir. Can everybody hear me?
Yes, we can.
Excellent. Good morning, everybody from the U.S. My name is Russ Roberts. As Hector just said, I'm the Vice President of Business Development for Hanoi Phaser. I've been part of the Phaser team for about 8 years now, way back when we were a much smaller company. And I'm going to discuss our enterprise-grade active electronically steered antenna for Satcom on the move and how it addresses interoperability today and is ready for the larger picture tomorrow. Before I get into the antenna, I want to spend just a second talking about Hanoi Phaser. Hanoi Phaser began as Phaser Solutions back in a shed in 2005, putting together an antenna idea for UK rail mobility. In 2005, there wasn't a lot of Satcom communications going on for comms on the move, so this was a novel idea, and it took off. With some funding and some first prototyping, they were able to develop the first KU band comms on the move Asic, which was developed and eventually was acquired by Hanoi Systems of Korea, who has brought it forward from a startup R&D operation into a full-fledged manufacturing and antenna delivery organization. Hanoi Systems has a much bigger picture on the space front. They are also involved in launch vehicles. They recently invested very heavily in OneWeb. They produce satellite components. So we're just a part of a larger picture, but our footing is very strong. When Hanoi Systems acquired Phaser in 2020, we had 9 employees. Through the pandemic and a year and a half, we are now up over 70. We have a full manufacturing operations capability, and we're managing the supply chain risk, which we're all facing with silicon shortages as we scale up from that R&D into manufacturing. We have opened an Asic Center of Excellence in Cambridge in the UK, as well as my office here in the US for business development. We're working with two of the world's best fabricators and have just entered into a manufacturing agreement with Plexus Corp to assist us with manufacturing readiness and to get the antenna ready to go to market. So about the antenna, why would you choose the Hanoi Phaser antenna over all of the others we're talking about today and all the others that aren't on the panel? Well, you'd want to do that because our antenna has more active capability per meter than anybody else. Virtually everything under our radome is part of the active component. It's not wasted space. We've decided to release our first product for maritime because it is a very challenging application and it will really put our antenna on trial to see exactly what we can do. The Hanoi antenna is an enterprise grade antenna. We're not targeting the consumer market. Just as you would use a large Cisco router for an enterprise grade data center, we want to use the Hanoi Phaser ASA for enterprise grade communications. How do we address interoperability? Well, interoperability starts at the base, and that is our ASIC. Our ASA has to work in a variety of use cases and in situations, not just in the LEO-centric world of tomorrow, but in the geocentric world of today. To be really interoperable, we have to be able to work with GEO and LEO and MEO. But right now, the focus should be GEO because that's what's available. Sure, OneWeb is in process and we're working with them as well. But right now, GEO is the focus. And that starts with our ASIC. Now in the 5th generation, our custom designed transmit or receive ASIC, there's one of each, operates in an analog form. And what we mean by that is all of our beamforming, steering, and RF is conducted in analog. We receive the KU band signal, or if we're transmitting the other way around, and down convert it all the way to baseband I and Q. We skip L band, we skip IF, we go all the way to baseband I and Q, and then combine the I and Q on the board, which I'll show you in just a second, to do the baseband beamforming phase control, combining, and all of the other functions that happen at the ASIC. Now, this means we don't have a buck or an LNA. It all takes place on that little chip. This allows us to use a lot less power than a fully digital solution. We do use more power than a traditional parabolic, we recognize that. But this hybrid solution gives us a little bit of both worlds. So to take this to the next step, we take the ASICs and we combine them. And for some reason, I've lost my mouse, I apologize. We combine the ASICs into what we call a core module. Each core module consists of a top board, which you can see there at the top, and a processor board at the bottom. In between is a cooling plate. This sandwich of PCBs allows for structural support, thermal management, and it can be curved or conformed to reach over top of an aircraft, or if it needs to be curved for a ship's hull or something of that nature. But primarily, this modular approach enables us to scale the aperture up or down to meet the mission or link budget requirements of the end user or mission or consumer. Really, one size does not fit all in the antenna world. You wouldn't buy one size of parabolic. Why would you buy one size of flat panel? We take the core modules, we scale them up into an aperture. This image you're seeing now is of our M6 or 6 module test platform. It's on the live range out in Essex, UK, doing on-air testing. In this particular configuration, one aperture is transmit, one is receive. There are several different configurations of the antenna, which I'll talk about in a minute. This one happens to be separate. Let me take the hood off here, take the bonnet off, and talk about what's underneath the hood. So underneath the radome, you find a complete antenna. There is no antenna control unit that is embedded within the system. We're operating in standard L-band, modem agnostic, open AMIP interface. We have our own built-in dual GNSS and INS receivers. So the antenna knows where it is, where it's going, without any need for external PNT data. We will accept external PNT if necessary, but we really don't need it. As you can see, this particular antenna makes up 6 modules. Now we can scale that up if you need more modules to equal more aperture, which equals better gain, or scale it down if you need a smaller antenna. As with all flat panel antennas, there is no moving parts. It is completely solid state. The line replaceable unit is the antenna itself. If it breaks, you take it off, you put a new one on and move on with your mission. No spares, no spare parts, no belts, no drives. Sounds pretty familiar. So what do I mean by scalability? Well, let's meet the family. The antenna is going to be available in at least 4 different configurations, probably more than that, depending upon what the market requests. The leftmost image there describes what we call the SNG configuration. If you're running around in an SNG vehicle and you need a lot of transmit gain, then we scale up. That's a 1.1 meter transmitter with 5.6 dBW of EIRP. On the receive side, you have 10 core modules. That's 13.9 dBk of G over T. And as you can see from the image, we can scale that up or down. Different configurations mean different things. The far right configuration is 13 or 1.1 meter transmit and 1.1 meter of receive, which is at this point with our release 1 product as big as we can scale it logically. We want to talk about performance. That's always the key question. With our antenna being modular, we can scale the performance up or down as necessary. But an example, if we have a 10 module configuration, which is approximately 90 centimeters equivalent, operating from bore site, you have an EIRP of 54.2, which for a flat panel antenna with no buck is really pretty impressive. Out at 70 degrees, which is our limit of theoretical operation, 47.2 dB of EIRP. And you can read the G over T figures here as well. The concept of operations allows us to make the antenna larger or smaller to meet your needs, not necessarily make your link budget fit our antenna. This has proven to be rather popular. When we were at Satellite this year, a lot of people were asking about how to make this work. So kind of in summary, I'm going to keep this really short. What makes us different? Well, we are the lowest profile antenna at only 7 centimeters high. We operate at extremely low look angles for working on the entire GEO arc today and the LEO arc and mesh tomorrow. Modular and configurable, we can make it larger or smaller. We are fully ready for LEO today with near instantaneous beam switching with our product. The follow-on products, which we will talk about when we have more information on them, will feature Multibeam, KA, Aero. We're working on a multi-frequency solution down the road, but for right now, a single beam, KU band, near instantaneous beam switching, high-speed tracking, and we work with literally any orbit up there. And because we are focusing on GEO today, we are optimized for GEO, HTS, and comms on the move. You know, the satellite comms on the move market is changing very rapidly. There are new products and technologies coming from all corners of the world and some of the best minds in industry and academia. And everybody has a place. I don't think there is any one best antenna. I think we all have our spots and all of our segments. Hanoi Phaser has set its technology for the enterprise segment, and we're looking forward to delivering the release 1 antenna in early 2023 with follow-on antennas coming along in the subsequent years. Thank you very much for your attention. I hope I kept this brief enough and kept your attention the whole time. If you would like to reach out to me, my address is there on the screen, and I look forward to seeing you at a trade show soon.
Well done. Well
Thank you,
done.
Doug. We do have a question. What type of power consumption do the configurations have?
The current configuration, the one you see there on the screen, uses about 900 watts per side. That will improve over time as we move forward with generational changes. We recognize that 900 watts per antenna is a bit of a load, but it is still about a fifth of what you would find from a full digital solution.
We have another question. How do you create multibeam not being digital?
We do it through analog beamforming. The ASIC itself is configured for multipath. We obviously have to create different data channels to separate the I and Q once it comes off the ASIC, but it is done within the ASIC and the analog hybrid steering.
Okay, and I believe that there are no other questions from the audience. You make reference to release 1. I presume that implies that there is a release 2.
There is a release 2, a release 3, and more to come as we continue to develop follow-on technologies.
Okay. Thank you very much, Russ. So we'll move on to the next presenter, and that will be David from Celestia. And the presentation is entitled Multibeam Gateway Antennas for New Space. David?
Unmute me. Good. Are we? Yeah, I think we all should be working.
It's working.
Hi. Good. Thanks. Just a second. We don't seem to be. There we go. Thanks, Barry, for inviting me again to this. I've been here before, and it's been a great conference, and well done for doing it. I'm here to introduce Celestia UK particularly, and just give you a little bit of background to Celestia, because it's not a very high profile group, despite a very long history and breadth and depth of expertise in the in most of the technologies associated with satcoms and satellites in general. Celestia UK is the UK subsidiary of a European group called Celestia Technologies Group, and at the group level, there are most of the companies are spread around Europe, as you can see from the dots there, with one outlier in California. And Celestia UK is the UK subsidiary of it. The group is headquartered in Netherlands. There are 15 of those subsidiary companies, 7 of them in the EU, and ourselves here in the UK, and the one in the USA. The turnover, to give you some idea of the scale, is 36 million euros last year. And between all the group companies, there are around 240 employees, but a very high, unnaturally high percentage of them are degree level engineering people. It's a very technology oriented group. And this is a matrix of the companies that are spread around. Celestia UK is there in the top center, but they're covering, as I said, a wide range of technologies, from satellite test systems, cryogenics, RF LNAs and HPAs, TT&C systems, modems, and indeed some MIMIC design work. There's not many parts of satcoms that somewhere in the group is not addressed, and the group and the individual companies do all work together quite closely, in fact. But with respect to Celestia UK, the headquarters of the UK part is based in Edinburgh on the Heriot-Watt campus. And we have a secondary facility in the Harwell Space Science campus, which is just in the south, just outside Oxford. The UK part was established in 2017 with the prime objective of addressing the electronically steerable antenna markets. And that's both gateway terminals and user terminals. But in addition to that, we're also doing some work on PNT systems, position, navigation, and timing. And to do that, we've got at the moment 30 engineers, again, very technology oriented. And of course, as I said before, we work with the other members of the group quite a lot as well. So there's a lot of background support. the activities were include user terminals, as I mentioned, the aeronautical antenna on the left there, and a connected car solution at Ka band. But really the main focus and the majority of the effort is going on the gateway multi-beam antenna. And that's a conceptual picture of it, where you have a relatively small block like that, which is effectively that will support. Well, it's very, you can cater it for what you need according to the constellation that you have. But for example, you could easily have 20 independent beams, and each one of those beams will support a full 250 megahertz of instantaneous bandwidth, and it's absolutely flat. So it's good traditional gateway spec capability, but all of them are completely independent, and of course you need that for the forward carriers particularly. But associated with that is the new systems with NTN architectures, non-terrestrial networks, which is associated with the drift of our industry towards 5G and much better compatibility. And we're very involved with that to move in that direction. The main two areas for this is a general E-scan antenna, we call it, which is for the digital ground gateway for all of the constellations, the smaller EO ones and communications ones. But we are also engaged with OneWeb for their second generation multi-beam antenna. And I think we are. But as I say, the drift really is towards new space, where new space we see as this new era that's been described already, where there's hundreds of constellations and thousands of satellites moving all over the place, which is a completely different concept, and that's going to result in many more ground stations being required. And if you have inter-satellite links, that's not so intensive, but in many cases, you do still need a lot more ground stations than are currently perceived. And you need that for the global coverage. You need it because the frequencies at Ka band, you need it for the diversity, weather resilience, and just general hardware resilience or physical attack of some sort as well. So we see a lot of new ground stations being needed. And each of these ground stations now are a lot more complex than the existing standard teleport. And so the equipment that goes in it is more expensive, more complicated than we're used to. And that has an increased capital cost, obviously. So there's more terminals that are each more expensive. And with the more complex systems, you're going to need more skilled, more highly skilled operation and maintenance staff. And so the operational cost to support this enlarged number of more complicated teleports is very significant. And so we see the drift really towards away from that general architecture and more towards a centralized teleport system, where you essentially are trying to take away as much as you can from the remotely located gateway terminals. So you're going to be left with the apertures and the LNAs and the HPAs. But beyond that, you could conceive of bringing back the RF signals to a single centralized, secure, highly redundant, well-staffed hub where the whole network is run from. And so it reduces the investment required in the remote terminals. And all of the equipment, the modulation equipment with all its redundancy is located at this one single location, which is somewhere nice where people are happy to live. And you've got lots of fallback staff, all who understand the technology very well to keep it all running. But of course, that requires, basically it requires bringing the RF back, generally over IP networks, private or public, which is now all possible. And the consequence, the object is to reduce the antenna is a key part of it. It's going to reduce the real estate requirements, reduces the hardware requirements, and it makes the operations a lot easier with everybody in one location. Of course, it does need the excellent connectivity at RF between the antennas and the centralized hub, and that depends on the RF over IP. But really, the fully electronic multi-beam antenna is a very key part of this new architecture. And while we're involved with the rest of this virtual networking arrangement, our main focus, certainly at the moment, is on the electronic multi-beam electronically antenna. And that's what we're really focused on, with a to look towards a global networked teleport system as things will how we see things will evolve. And I think that was a quick introduction of who we are and what we're doing. This equipment will begin to appear next year, and my contact details are there. I'd be happy to talk to anybody now or offline. Thank you very much.
So, thanks very much, David. We do have a question from the audience. Okay. The aperture of the gateway antenna looks unusually small. What is the innovation behind it?
I think the aperture size is, I don't think you should read too much into the graphics there. The aperture sizes are, it can be made to suit the requirements of the particular constellation. The link budgets do work. We work closely with the constellation people, and the EIRPs and GOVTs are consistent with what they need. And we can make the aperture bigger or smaller as required. Sorry, what was the last part of the question?
What is the innovation behind it? So I suppose what you're saying is
really the ability to cover. Thanks, Hector, for the fact that you are really supporting a large number of beams, all of which are full 250 megahertz or so bandwidth at very high performance, and all of them electronically steerable from a single small installation. It's the multi-beam full bandwidth aspect is non-trivial, and it does require quite a lot of careful system design, and it is quite a complex design as it ends up.
We have another question that I think is tightly connected to that one. Regarding RF over IP, bandwidths are likely to be very high. Is this work you're looking at within Celestia, or are you working with partners to provide it?
A bit of each. We are working a lot with partners, particularly people who have the more expertise than us in the actual RF over IP, but more particularly with the people in the well-established players in the teleport services business who understand the requirements and how it's going to go. And so we're working with them very closely. As I say, our focus is more on the antenna at the moment, but it is we're very tightly engaged with the wider requirements.
And I have a question from my side. Is Celestia interested in developing the solution, or are they also looking at providing the service?
we're looking at the solution at the moment, because really one of our partners is, in fact, more than one of our partners is in the service provision business, and so it's not really, we are partnering with them, and so we won't ourselves be providing that service. The idea is to support them in providing the service. Yeah.
Thank you very much.
You're welcome.
So we move on to the next presenter, that's Bill. And the presentation is entitled Trending Requirements and Key Product Characteristics in GSO and NGSO Phased Array Antennas, ThinkScom perspective, and obviously Bill is from ThinkScom. Bill? Are you there, Bill? We can see the presentation, but we can't hear you.
There we go. That should be better.
Good.
All right. Thank you. Thank you, Hector. And good morning, good afternoon, good evening, as the case may be. I'm Bill Milroy. I'm the chairman and CTO of ThinkScom. We're located in Hawthorne, California, where it's right now definitely good morning. It's 5:15 in the morning, but it looks like we're going to have a beautiful sunrise. So appreciate the opportunity from Barry to the invite to present here. I think this is a really interesting panel in terms of Barry's been able to bring together a really diverse but also very deep group of presenters, and I'll do my part here. The main thing I want to do is to touch upon kind of the industry as a whole, and then from there I'll talk a little bit specifically about ThinkScom products and the way we're evolving in this industry. So as has been mentioned by several of the other panelists, the industry right now is very much in transition. Not, I wouldn't say necessarily from GEO to LEO, but adding LEO to existing GEO systems. So we don't see GEO systems going away. That's our opinion. LEOs are going to augment them. Each of them has their own attributes between GEO and LEO or NGSO more generically. And there's certainly a lot of players in here, different frequency bands. But we think the key from a terminal standpoint is that you need to be able to operate on all these networks. We don't think a GEO-only solution or a LEO-only solution is the way to go. And so at ThinkScom, we're trying to work both of these markets, and I think we've been somewhat successful, but also to provide good, not just okay performance, but the best performance in each of these areas. So this is in terms of all the different parameters specific to NGSO. This happens to be NSR's own tool, which I highly recommend, is very useful. But you can build your own LEO constellation or put a LEO or MEO constellation in, and it gives you all the important metrics. Now, based on the orbital altitudes, the constellation sizes, and such, the important things for the terminal would be the minimum elevation angles, the beam coverage footprint. Talk a little bit about latency. Of course, depending on the LEO or MEO, you have superior latency in terms of lower latencies, and then RF interference considerations. So there's many more knobs to turn, if you will, with respect to NGSO constellations. And a terminal that's going to work across all these needs to be able to adapt to all the different nuances of the different systems. So I thought it best on this chart to actually go into what are some of the key drivers in the terminal. And these are sort of generic drivers, but I've circled it. In any given system, we have things like area or taper loss, spillover loss, or blockage loss in some systems. But the main items here are really the ohmic loss. By this, I'm referring to the front end losses in front of the LNA, and then the noise figure of the LNA itself. And taken together, these are really the main drivers to the overall G on T for a given area system. So I've put the typical metrics on the left here with respect to a parabolic. So a parabolic generally has low ohmic losses. It may have maybe a dB of taper loss. And then in terms of noise figure, this happens to be a KU band example. It's pretty easy to get a 0.7 of a dB noise figure LNA. The sky temperature is pretty generic. And when you all roll this up, we get a reference performance level. AESAs in general, and I don't mean to pick on any or be specific, so I put large ranges in here. Some ESAs can enjoy not having any taper loss at all. They can be uniformly excited. There may be a thinning loss. Some ESAs employ this to reduce cost and power levels. And the front end ohmic losses are based on the architecture, whether you have one LNA per element, whether it's a dual pole element, whether you're perhaps sharing one LNA amongst 4 elements to reduce cost. But generically, these would be in the 1 to 4 dB range, depending on what we're talking about. And then the LNA noise figure, again, there's a lot of good work being done in this area, but because this is a mimic, so as an example, KU band, we might have 100 cubic inches, a really large area available to package and optimize a discrete LNA. So this is, a hand-sized, fist-sized LNA. However, in an AESA or an ESA, the challenge here is you might have less than a square centimeter to package that unit. So generally, that's going to be an RFIC, a mimic LNA, and some of the constraints there, then that limits the lowest noise figure that can be achieved. So this is a 1.8 dB. Maybe some people are getting down to 1.6 at KU band. A good number is 2 to 2.2 dB at KA band, but it's a much more challenging situation because it's a much more compact structure. And then another factor with respect to ESAs, not with parabolics, but with ESAs, are the scan loss. So this could be a scan, a cosine to the 1 power, a cosine to the 1.3 power, a cosine to the 1.5 power. But this is the loss associated with scanning. So taken together, these give you the overall attributes of the phased array scanning system. I want to point out here, and I'll try not to be too salesy, but these are the metrics, those same metrics for our ThinCom fixed array. So depending on frequency band, our losses are much lower, typically in the 0.4 to 0.9 of a dB front end loss. And the way we do that is we use a parallel plate transmission line. We don't have any phase shifters. We use a parallel plate air-filled transmission line. So our losses are very small, in the order of less than 0.08 dB per foot at KU band. So when you, for 1 foot to 3 foot or 75 centimeter size, we only have a few tenths of a dB of total loss in the structure. And because we use a centralized LNA, we can use the same LNA that you would use in a parabolic dish and enjoy that. The other thing that's a little unusual with our system is that as we scan it, it's a precision cosine to the 1.0 roll-off. And the reason for that is the aperture efficiency, the excitation is constant. So pointing out that in general, as a rule of thumb, every 1 dB of additional ohmic loss drops the G on T by 2.5 dB per K. Every 1 dB of added LNA noise figure drops the G on T by 2. This gives us a huge advantage, anywhere between a 4 to a 8 dB advantage on an area by area basis. And that's really, we think that's a real key and perhaps one of the reasons that we've enjoyed a lot of adoptions. So this, in the spirit of show me the data, this is one of our units here. This is a 60 centimeter receive antenna. And what's interesting, consistent with what I just showed you, the G on T of this, which is shown here, 17.5 dB per K G on T, that's about the same as a 75 centimeter parabolic, even though this is only a 60 centimeter receive antenna. And then you see here the roll off. This is all measured G on T of the antenna. You can see how it drops down, but this is a cosine function. And you can see that we're actually able to operate. We can still close links at lower modulation codes at 10-degree elevation angle. This turns out to be very important on any vehicle that moves, particularly aircraft, plus to be able to work on geosystems up at very high latitudes. So this is again an important attribute, the G on T. This really is the main driver for the performance on the forward link of most systems. So side lobes, as an antenna guy, I feel like I have to show some measured patterns. These are measured patterns at 30 gigahertz for the transmit antenna that's in that antenna. That transmitted antenna is about 40 centimeters in diameter. So what I'm showing here is a complete upper hemisphere chart. So here you can see the main beam, but and here you can see the main beam. This is scanned at 75 degree scan angle from zenith, 15 degree elevation. This is at a more shallow angle. But the key thing is here is what you don't see. These are all, this is the noise floor. This is a minus 40 dB floor. And what you notice is there are not any grading lobes, or there are not any side lobe structures. And this is becoming increasingly important because the regulatory environment, the interoperability environment is becoming so complex now as we move from a GSO plane concern only to an NGSO. NGSO satellites, of course, can be anywhere in the sky. So your any side lobes you have in any location can hit something. And to make things even worse or more challenging, these frequency bands, in case of Ka band, which would be the 27.5 to 30 gigahertz band, these are the same frequency bands that are also being used for terrestrial point-to-point services, that or referred to as the 5G millimeter wave band. So we have NGSOs competing with each other, we have GSOs competing for the same band, and we have terrestrial users. So what does this mean as an antenna guy? It means you have to be really careful in your side lobe structure. And so as an antenna designer, this is something we spend a lot of time looking at to make sure that we provide the best, lowest side lobes, the best interoperability amongst all these challenges. So on the aeronautical side, there are, of course, both commercial and military applications. In the case of our own system, we have about 28 million flight hours of our KU system that's flying under the GoGo, now Intelsat 2KU system, so flying on various airlines as shown here. Those systems are, reliability is just so important for all applications, but particularly in the airline industry where it takes a lot of time to remove the radome on an aircraft and service or replace an antenna. So we are bringing by experience now, we have 100,000 hour or higher MTBF. So this is an extremely unusually reliable system, if you will. We have many, we're on 1,550 aircraft, and then our Ka band systems on about 300 aircraft, both commercial and military. Some of the early adoptions of that are on for Spirit Airlines, Air Canada. We are approved for GX and Hughes operation on GX Plus North America. We're the preferred solution but for Inmarsat GX's system. We just had a press release out that Panasonic has adopted our system for Panasonic in-flight connectivity. And of course, we're already the incumbent with Intelsat. And we also are line fit operable. That's line fit means that we can actually be included as standard equipment from a Boeing, when you buy a Boeing aircraft or you buy an Airbus aircraft. So the proof for interoperability, we're really walking the talk, we think, in that area. So we are on all the different systems I just mentioned under GEO, but on LEO, we've been up on the Telesat LEO constellation. Telesat recently announced that we are the first aeronautical antenna that will go on the Telesat Lightspeed system. That service will start in 2023, and not really, we can't take the entire credit. We bring a very high performance system, but of course there's many things that go into that. But Telesat's own estimates is that we'll be able to do 830 megabit per second down and 200 megabit per second up from each aircraft on the Lightspeed network. We also are working with OneWeb. It was just recently announced that working with Panasonic, that system will be a LEO-MEO compatible system. We've actually done some early demonstrations in Melbourne, Florida on the OneWeb constellation. We will be compatible with Inmarsat's HEO network. That's a highly elliptical orbit system that is another way of to get polar coverage, which is very important to the airlines, but pretty much important to everyone else. And then we actually have flown, we've taken our antenna, gone on a very small business jet. We've done O3B, MEO, and SCS GEO interoperability. So the whole point here is to be able to roam between MEO networks and LEO networks, consistent with what everyone's been talking about today. So looking forward to the future, well, and actually a little bit of the present, there's a growing interest in being able to take antennas and embed them inside an airframe or inside, it could be a vehicle as well, but I'm talking specifically here about aircraft. As it turns out, we've been embedding our antennas in aircraft for some time for government applications. And we've been approached by the usual folks in the commercial airline industry and asked, could we embed our antennas, the ThinCom antennas, inside? So what do you need? What are the attributes you need to be able to embed inside an aircraft? Well, you need to be highly reliable, because obviously access to this antenna is not going to be easy. Second, you need to be very, very efficient, because there's not much space here. It's a very constrained, these individual cavities are highly constrained. And of course, we need to be very thermally simple, or low thermal loading. So we need to consume very little power. And obviously, if we were to create a lot of heat, this could become a really big problem, maybe even a danger in an embedded installation. So we bring all those attributes, the low power, the very high efficiency, for the reasons I mentioned. And so for that reason, we are currently embedding our antennas in several government applications, and we will be embedding them at some point here in the not too distant future for commercial aircraft applications. So on mobile markets, meaning on the move, a couple things here. We have our ThinSat 300 product, which is a KU band on the move system. We have about 300 of those out in the field doing various enterprise and government comm on the move, first responders. That's about a 10 centimeter high system, capable really 75 centimeter parabolic dish equivalent. So we're able to do 8 megabit per second on return links. This is a 20, 30, and 44 gigahertz government system, VIX-based. This is a 20 and 30 gigahertz, very rugged, highly ruggedized KKA system that we've constructed for the US Army for the DESTA program. And then these are in terms of what we're doing right now, and that's what kind of Barry asked us to do, is what show us a little bit into what's going on in the very near future. We have a KKA band system, which is really intended to be the KKA version and improved version of our KU band. And I think it's important to point out Q and V band. So we're actually working on a dual beam Q and V band system. We see that the market appears to be moving in that direction. Again, I don't think Q and V band will replace KA band and KU band, but it will augment it. And there's 10 gigahertz of baseband available at Q and V. We can already see this beginning to happen in filings. And as this for gateways or teleports, Q and V is is actually being used today, and it will be used in user terminals in the very near future. On space payload antennas, we actually will be flying or orbiting our first ThinCom payload antenna. So it turns out all the attributes I talked about in terms of being very low power, very compact, highly reliable, lightweight, these are all very important attributes for all satellites, but particularly for smaller satellites, CubeSat type satellites. So 3U, 6U, 12U kind of satellites, this is important. And of course, having power, we think this is a recurring theme, but on a very small satellite, these are very power limited, to say the least. So that it's key that for every watt you use, you don't use it up in terms of dissipation in electronics or dissipation in the HPA that drives it. And then gateway antennas, as was mentioned in the Celestia presentation, we think this is a really exciting market. In fact, we were awarded the Satellite Technology of the Year award back in 2019 at the satellite show. That was the 2020 satellite show. So we concur that this is an exciting market. This gateway as a service or ground stations as a service. So same thing idea here. We use our same very compact, very high efficiency phased array antenna, that VIX antenna, and we combine those together, and that allows us to, on a software defined basis, reconfigure the antenna on the fly. So we can be a 7-meter parabolic dish when we need to be, but when we don't need to be a 7-meter parabolic dish, we can be 4 3-meter parabolic dishes, and we can move back and forth through that. And particularly for NGSO satellites, the link budget is so elevation angle and slant range dependent. This is a really important feature, and we think this is where the market's going. We're getting a huge amount of interest in this. It's really very exciting. So let's just check back on what you really need in these systems. We talked about the goal here, and everybody, I think all our presentation plus those of the other panelists have really emphasized this interoperability between LEO, MEO, and GEO. And we've touched upon some of the things that are required to do that. We've talked about reliability. We think reliability is such a key to OpEx of these systems in terms of not requiring service, not requiring removing radomes, not requiring replacing equipment. Reliability is very, very important. Size and spectral efficiency. Well, this is a given, and we talked a little bit here about the specifics of what drives spectral efficiency and size in terms of losses in the system, the noise figure of the system, the front end losses. We talked about power, how power is important on everything. It's limited on ground vehicles. It's been limited on UAVs. It's very limited on satellites, particularly small satellites. But even if you have power, you then have the issue of dissipation, thermal management of the system. And there's nothing, nothing worse than having a system that works well, but creating a lot of heat so that the reliability of the system is brought down. I brought up minimum elevation angle. That's important on any constellation on a moving vehicle, and very critical on geo-based systems, in which case you want to be able to operate at the higher altitudes, and wide instantaneous channel bandwidth. Everyone's moving to these wider bandwidth systems. So moving forward, we think that there's a trend to higher frequencies, QV and W band, wider instantaneous bandwidths to accommodate these wider waveforms, dual simultaneous beams when they're needed, smaller and lighter variants. I already touched upon the embeddable portions, or the markets that are moving towards embeddable systems. And I mentioned these regulations. I think this is going to be really a big deal over the next couple of years as more satellites go out, is how do these systems, how are they going to operate interference free? How are the service providers going to mandate that? And how are the regulatory agencies, the ITU, the FCC, going to handle and dictate how interoperability will happen in the future? So with that, thank you for your time. And if we have time for questions, I'll leave it up to Hector.
Thanks, Bill. We have two questions from the audience. With OneWeb circular polarity and most GeoKU being linear, how does the antenna handle this without changing the terminal? Being able to not swap and use LEO and GeoKU, take the dB loss and not switch equipment?
Sure. So I'll give an example, an aeronautical example, IFC. So we have, as I mentioned, some 1,600 systems flying right now that are tracking linear. So they can do V or H pole linear KU band. OneWeb, as an example, is a KU band system, as is Starlink, both of which use circular polarization. So we are developing, this was just announced a few weeks ago with Panasonic, a variant of that antenna, that KU band system, that will be able to do both linear and circular polarization. So we'll be able to switch between both of those. So we'll be able to accommodate both the linear that's preferred for the GeoKU, and we'll be able to accommodate the circular polarization that's preferred for the NGSO KU.
There's another question. What are the cost drivers for a flat panel antenna? And I believe this should be specific to the VIX configuration.
Sure. So the VIX array is made up, in the case of the aeronautical, is made up mostly of aluminum and air. So we don't have feed throughs, we don't have phase shifters, we don't have any pick and place. So it can be made in volume, inherently low cost. And in fact, we're even looking at additive manufacturing, particularly for space payload antennas where weight is so critical. However, we also make our antennas out of plastic. So we think in terms of scalability, that is, can you bring your manufacturing costs down as a function of volume? The answer is yes. So obviously I'm going to be a little bit imprecise in pricing, but we believe in the consumer market, we can field VIX-based systems that are in the sub $1,000 range. We think it's difficult for us to get much under $1,000 per integrated system, and that would be in quantities of 100,000. We think the sweet spot there is really in the enterprise market, which requires higher performance, is tolerant to a little bit higher price, but is more in the 20 to 50,000 unit per year. And that market we're concentrating on right now. We're working with contract manufacturers, and we have successfully built and actually sold as products injection molded plastic versions, very much kind of Barry talked about the Spherical and also the early work with Fortel. Fortel also did a lot of work with metallized plastics that we of course, that was some time ago. And we've shown that we can build these in very high quantities, VIX-based antennas in very high quantities using metallized plastic. And that's a great way to bring down cost.
We're running a bit late, but I'll take the last one. What is the typical power consumption for the KA2517 Aero terminal?
So the antenna itself, not including the HPA, which we use a centralized HPA, is in the order of about 50 watts average, and can get up when we're scanning at very high rates. And we can scan that beam. We can move the beam anywhere in space to anywhere else in space in about 400 to 800 milliseconds. It's very agile. Then we might consume about 200 watts while we're slewing the beam. So 50 watts average, 200 watts peak.
Thank you, Bill. We'll pass to the next presentation by Steve from NXT.com. And the presentation is entitled NXT.com, Changing the Way the World Connects. Steve, you've got the floor.
Can everybody see my screen?
We can.
Great. I'm always confused by what screen's being shown. I feel like I have. Good morning. I'm Steve Newell with Nexcom. Nexcom's a startup company based in Georgia, and I'm the Chief Commercial Officer. Nexcom was formed effectively 2.5 years ago with the sole purpose of providing electronically steerable antenna technology based on the fragmented aperture to provide the most efficient and effective antennas that are available today. Unlike some of the other presenters, we target specifically the defense and aerospace markets. It's kind of an interesting sidelight in that we have 3 founders, one of them which spent his life in commercial airlines, one of which spent himself in defense and business jets, and one of which spent his entire career in maritime. And when we had to pick something, we didn't pick maritime. So we've got a very good team in our CTO, Carl Novello, and our founder, Dave Horton, that understand these markets, and that's what we're focused on. And as I tell people, LEOs are made great by ESAs, and ESAs are made great by LEOs. And hence we see the coming LEO revolution and are focused on delivering products for that market. We have clear routes to market with all of our global industry leaders, and we've already announced a key win with L3Harris in the defense sector in KU band development, and we have an undisclosed one in KA that we can't announce, but it's happening simultaneously. So people ask, what is a fragmented aperture? And in homage to Barry's Spherical squirrel antenna, we'll go diamond shaped. But this is a unique pattern that had been conceived and developed probably 20 years ago by the Georgia Tech Research Institute that looks at element structures of the past and says, well, if we more finely optimize these using high-speed computers and some very sophisticated modeling, we can reduce a lot of the effects associated with the classical patterns, whether they're a dot, a square, in this case, I show an iron cross, and we can model out defects from these patterns in ways that are specific to an application or specific to a frequency range. So there's a model that does that, and that model's got 1,000 degrees of freedoms or so that define outcome constraints, all the variables and all of the design goals that you want to put into, and through a genetic algorithm. And the genetic algorithm say we're going to make something, test it, make something else and test it, combine the attributes of both of them, continue to test sequentially through a series of natural selection to optimize those degrees of freedoms, and you end up with a structure that is complex and looks sort of like your 1980s Space Invader-y looking thing. And for those in the know, that is not the pattern that you would see on our apertures. That's just a simple one that sort of denotes what they look like. Highly pixelated, 64 elements on a side that are then an array of mini arrays to provide the most highly efficient apertures we can build. As a result of this genetic algorithm and it's running its paces, the resultant elements are radiators that are not resonant structures. And because they're not resonant structures, each one of these elements isn't stealing gain from its adjacent friend, and which makes them inherently wideband. We maximize gain for a given area, and as a result of it, it uses less power. And I'll sort of re-hit those points here again. More gain means lower power for us, and lower power means less heat to dissipate. And because we're inherently wideband, all of that dynamic bandwidth is equal to our instantaneous bandwidth, which for us is the entire band in KU and KA. So when we look at these things as limitations here, they're limited to the systems that they're supporting, and typically that means the modems that are only capable of some level of instantaneous bandwidth. So I see this as outperforming current modems and allows us to afford multi-satellite operations. What we're doing today sort of outperforms any of our market peers in terms of performance. I say we're, when asked what that competitive advantage looks like, I'm saying we're, have twice the performance of people that are currently in the market. So half the size of existing terminals that you can buy today that are ESA performers, and 1/6 the cost of some of our friends that are extravagant in their cost structures for defense applications. So both those things are Nexcom's advantages going forward. Like all of our brothers, we get to look around and take advantage of developments that have happened in the industry over the last 10 years. And one of those has been in the beam forming ICs and the commercialization that has happened based on the great things that have been done in the 5G cellular world. Nexcom's, shows up to the market. We can evaluate the best chips to use in our solution, and we have. And we have the state-of-the-art beamformers that we can buy off the shelf and meet the cost targets that we need to do to participate in the defense and aerospace markets. These things, there's one chip for transmit, one chip for receive, and currently, they allow us to do polarity switching inside of the chip, and one chip generates, as Bill was kind of say, these are the LNAs, these are the power amplifiers, and that's how we build antennas, that are fabricated on a standard PCB using standard PCB technologies, and not creating new physics as some would do, or working on the next breakthrough to build products. But there is one problem with these chips, and that it is the same thing that made them great in the first place, and they're based on 5G cellular and not satellite requirements. So in the vein of looking out to the future as to what these things will bring us, we expect them to get better in every dimension. They'll have improved power efficiency. The cost will go down by probably a factor of 10 in volume. Simultaneous transmit and receive operations in the same element, which is the hallmark of our fragmented aperture, will become a thing of the future. And I expect to see multi-beam operation without gain degradation as we split the beam. To Bill's point, they'll have an improved phase, improved noise figure, and hopefully improved phase resolution to more closely track the satellites that are in near Earth orbit. So all of these things I expect to happen in the next decade, and hopefully sooner. And all of these things will allow us to target new markets outside of defense and aerospace as the price of chips become lower. I mean, any of the active phase arrays will tell you, our single biggest hit for cost is the cost of beamforming ICs, and the single biggest hit to power are the same RFICs. So if we can make those better in every dimension, our products become better as time progresses, and it allows us to hit more markets and do more things. At the beginning of this year, we built the fragmented aperture. Once again, you'll see the same Space Invader-y looking element structure here, which is not the one that's the actual one that is specific to Nexcom. And quite frankly, it's RIP. You got to pay to see. We'll go with that. So this is an 8x8 element-based transmit test board. This subarray helped us validate all of the assumptions and RF performance that we expect to receive out of the element. It also combined all of the other features, whether it's beamforming control and beam steering and being able to shift between linear and circular polarization, how we control each of the chips, how they interface to the rest of the system. All of that was built into one board so we could reduce our technical risk and validate our performance models, and we did that successfully. These will be built into larger structures going forward to make them more, dare we say, Lego-like is the words of our CTO. So each element packed into a large subarray, a subarray with chips in a board that then can be combined into other arrays. This is not an uncommon methodology, as you have seen from other participants in this market, but this allows us to rapidly tailor a solution to a customer basis. In this case, we show how 4 subarrays get made into a 50 by 50 module, 4 of which goes into a very large flyaway aperture used to support geo operations today. So this is a product concept and to show sort of how that modularity can get stacked up. Not something that we're building at the moment, but something that could be built in the future. Other concepts look like smaller versions of that in KA. Once again, this takes on a flyaway form factor where direct pointing to a geo is beneficial to allow rapid rescan to a LEO for dual LEO geo operations, which seems to have a strong benefit in the military markets. More flat plate LEO only applications look like these concepts were the same flat plate structures put on vehicles. And in aviation, we modularized the same concept for transmit receive panel in a novel aperture that looks a lot like Inmarsat antennas of old to support everything from very small business jets to mainline commercial aviation. So these are the things that we think about when we talk about packaging, and these are the areas that we focus on. If it's defense or aerospace related, you can be rest assured that we're having pleasant conversations with lots of people to try to propagate our technology across a wide range of participants. Barry asked us to come up with some takeaways and some predictions for the future. I'm not going to cop out here and take 3 easy ones, but these are semi-provocative if any case. I do see that there'll be many LEO networks coming to fruition. And as Elon Musk likes to say, he'd like to be the one that doesn't go bankrupt. Having seen already a number of them go bankrupt and refocus and retool, I would predict that some consolidation will occur. And regardless of the end state for all of these future NGSOs, whether they're KU or KA, or as I like to call it, K next, which can be Q band, V band, W band, it doesn't really matter. It's going to be something after all these things get proliferated. None of it, and I mean none of it, will keep pace of our relentless demand for data. So the prediction there really is no matter what we build, it won't keep up, which is good news because we'll keep building new stuff. I would also predict that based on our current drive and market focus, that our technology will show up in many, many places with many, many different suppliers providing it. So, and that will allow us to drive a next generation chip basis, which will allow us to move farther down market from aviation and defense and significantly drive these AESA volumes for everybody, and not just us, everybody. And my last prediction is that we're going to continue to release products with new customers, and you'll see new announcements as they come around, whether it's KU, which KA and KU, which we currently have in development, KU with L3 Harris, and we'll see next generation of these as new constellations come online, whether it's from Kuiper or SpaceX or Hanoi or you name it. There's a lot being discussed, and we expect to see more in the future. And with that, give me a shout. We'll have a pleasant conversation.
Well done. Well done.
Thanks, Steve. We've got a question from the audience.
Time on
what about manufacturing tolerances to implement such small details at KA band? It seems really hard.
Yeah, it's hard. I agree. It's hard. It's hard for everybody. It's not just hard for us. Manufacturing tolerances on the fragmented array are within the ability of PCB manufacturers to make them. the trick on all of these things is you got to find the right PCB manufacturers to make them. Not everybody can do it, and the ones that can, we've had to discover, and they can do it just fine. And there's other details within the board structures that lend itself to cost reductions and novel improvements. And because it's on the inside of the board, you can't see it, but it's still there, and it still costs a ton of money to make. We've found other people that can help us do those details more efficiently. Yeah, as well. So I mean, that's it's a good question, because it does highlight, you know, limitations of technology. As you move beyond the KA and move into new frequencies, features on these types of structures become so small they have to be fabricated with lithography, chip scale lithography, not PCB scale. So we see a future on, you know, fully chip enabled products well above KA band that would have to be built, and they've been done in the past for military projects, but would have to be commercialized for future projects. But that's probably 15 years in the future.
Next question is, how do you combine digital control with RF circuits?
So carefully for one, because you're on the same board, it's spaced out. But we have done it, and we're going to continue to do it. So there's a lot of tricks on how you space board structures to ensure that one stays on one plane and one stays on the other, and they don't mix. Also, thing is that they're fairly out of, I'll say they're not out of band, but they're sort of out of reach for the typical harmonics that you see or are plagued with you know, those that incorporate digital beamforming and the true time delay chipsets that have, you know, frequencies that are running at SERDES. So they're literally in the same bands of operation that you're working with, but to a lower degree. We don't have that problem because ours aren't running at in the gigahertz realm, but they are running, you know, we do have to worry about those from a manufacturing point, and it's an engineering problem that's been well solved.
Thanks, Steve. We'll move to the next presenter, who is Honor.
Hi.
Alkan.
Yes.
The presentation is called LC-based phased array antennas for Satcom and 5G millimeter waves. Honor, you have the floor.
Yeah, thank you very much, Hector. Thank you, everybody. I hope you can see my screen.
We can.
Okay, great. So again, thanks for having me here. It's my pleasure to talk about our LC-based phased array antenna technology, which is convenient for Satcom and 5G millimeter wave applications. So I am Onur, one of the co-founders and CEO of Alkan Systems. So here we are developing this technology, LC-based liquid crystal-based phased array technology, which is convenient, as I mentioned, to get the signal from either from 5G or from the upcoming LEO constellations. So, and we believe, as you will see in the following slides, we believe, let's say, connected world, and you need such a technology which can actually operate with both infrastructures. So very briefly about ourselves. Alkan, we are located in Darmstadt in Germany, which is close to Frankfurt. So this is actually where microwave liquid crystal research initiated. So early in 2000s, my Professor Rolf Jacobi, he kicked off this research, and Alkan is actually a spin-off from TU Darmstadt after around 15 years of research activities. So the technology product I already mentioned, I think is more important, especially compared to previous the presentations, the markets that we are heading towards. So we will, of course, start with the enterprise market, which is a market, it's an existing market, and as a startup, we have to generate our revenues. But in the long run, we are actually focusing consumer and land mobile market, both on Satcom and 5G. And on the land mobile market, as I already mentioned, we believe you need a technology which can communicate with both telecommunications and satellite infrastructures. So having electronically steered phased array antennas, I mean, this is not an easy problem to be solved. There have been a lot of overpromises in the past, and at least last 2 decades, maybe even longer, people have been trying to solve that problem. So it's not an easy problem. And then today we have seen very innovative, very, let's say, good ideas and different approaches. So on Alcan side, I mean, since the problem is actually difficult, we are actually trying to solve this together with our partners. So we have our investors are our partners. They're also helping us on that. For example, one of our financial investors, CSS on the left side, this is the company which founded CST Microwave Studio. So RF engineers in the call, our antenna engineers in the call, they know this program very well. So we have actually great electromagnetic magnetic support here in Darmstadt. On the supply chain side, the Merck and BOE, so they are important for the liquid crystal panel technologies. So Merck is also located in Darmstadt. They are the largest liquid crystal manufacturer, and BOE is on the panel, the manufacturing side, and they are again world #1. And to develop a new product, we need a special hardware. We need a lot of customer interactions. So on that side, SES, which is, I believe, very well known, and MBS. MBS is a teleport located close to Frankfurt. They are also operating as an integrator. So we are working together and defining customer needs together with those partners. So this is briefly about Alcan. So how do we see? Actually, a few things will be repetition. So I am more or less, let's say, one of the last presentations of the day. So in the past, we know there have been a lot of a lot of LEO activities kicked off. They are either failed or they had to scale back. For example, the Global Star, I believe, one of the most famous one. So today, the situation is different. I mean, there is a new digital age. The companies like Amazon, Starlink, O3D, Lightspeed, Telesat, OneWeb, and many others, actually, they are working to solve and to come up with new LEO constellations, which is affordable, which will provide a broadband connectivity, especially for the people who are not connected. So, and we are big believers of that, and we believe, maybe not all of them, but definitely some of them will be successful. And what has changed since, let's say, the past? So today, first of all, the funding is available. We know that a lot of governments are supporting US government together with, let's say, they have been, they subsidized the SpaceX, Starlink project, Canada together with Telesat, UK with OneWeb. So that is, and China, for example, they are also in the game. So the governments are supporting. In parallel, the investors are started to invest a lot. So like Amazon is actually the good example. So the most probably planet's richest guy is actually investing into this technology. So the funding problem is solved. On the manufacturing and launch, again today in the early sessions, this is addressed. So satellites are becoming smaller, they are becoming simpler, and with the help of the new technologies, the satellite costs are reduced, and there are mass production satellite lines. So also the rocket technologies are developing. Reusability is a, let's say, the proven technology now, and with this they reduce the launch cost more than 90%. Still, the problem to be solved is the antenna on the ground side. As I mentioned today, we have seen very innovative approaches. So we are all, let's say, pushing hard to solve that problem. And we see mechanical antennas, we see hybrid antennas, we see fully electronically steered antennas. So each has its own trade-offs. We believe to open up new market to serve, let's say, to bring the connectivity to people who are not connected at all. Electronically steered antennas are important, and it's not only electronic steerability, but also the cost of the antenna is extremely important. So this is how we see the satellite industry. On the 5G side, there is a trade-off between the coverage and the throughput you can achieve. So if you want to cover the whole, let's say, landscape, then it's better to operate at the lower bands, but then the throughput will be limited. So to achieve higher throughput, now people are, let's say, step by step moving to the millimeter wave. So initially, the 5G is actually, it's already kicked off at sub-6 gigahertz, but millimeter wave frequency allocation is also already done in 2019. So basically above 24 gigahertz, depending on the locations, there will be millimeter wave services available in the near future. This will enable high throughput, several gigabits per second, but then the issue will be the coverage. So in order to solve the coverage problem, the high gain antennas are needed. High gain means, again, you need beam steerable antennas. So again, the cost of those antennas are important because, as I mentioned earlier, we are focusing on the consumer's side, which is the high volume market, but also the low cost market. So we are working in those two, let's say for those two industries, not because we can do it, simply because we believe we need ground terminals which can actually operate with both. So we already started to see consolidation in Satcom and telecommunication industries. For example, the British Telecom, OneWeb, they signed already an agreement to serve rural areas, to bring internet to the rural areas. Vodafone, AT&T, together with Space Mobile. So they are in the past, actually, experienced people in the call, they know this much better than myself. So the telecommunication industries, they have been running their own satellite programs. I think around end 90s, there have been these kind of programs, but they stopped and two industries were, let's say, running independently. But this merge is just started and we believe it will happen more. And when we were preparing those slides a few weeks ago, there was an announcement that telecom billionaire in Paris, he would like to buy, for example, Eutelsat. So those discussions are still continuing as far as I know. So those are just some examples. And there are new companies who are trying to bring, let's say, the services to mobile phones through satellites like AST, Link, and Omnispace. So we believe user terminals which can communicate seamlessly with both infrastructures will be key in the future. So as Alcan, our solution is to implement well-known phased array technology by using, again, well-known liquid crystal technology. So phased arrays, they are known since the 1940s. It's a proven but expensive technology. We see applications like in military or in aviation. So the simple result, I mean, the reason from our perspective is the technology used to achieve those phase shifts or, let's say, the smartness in the antenna. Basically, they're costly and they consume a lot of power. So we solved those two problems by using liquid crystal technology, which we know since 1970s from the displays. It's also a proven technology. And the production line is already well established for high volume markets. So we are merging those two to achieve the consumer markets both on 5G and Satcom. So in the past, we have seen that by introducing liquid crystal technologies, those bulky cathode ray tube based televisions becomes very slim, thin TVs. And if we have a look at televisions, actually there are a lot of components in the screen panels. There are backlights, color filters, polarizers, and so on. But on the antenna, first of all, we would like to achieve the same. We want to reduce the antenna form factor, the cost as well, and integrate this onto, for example, onto sunroof of a car. And our panels, actually, compared to the displays, are very primitive. The pixel size are very large. We don't need many of the subcomponents used in the televisions. Of course, on top of that, we need radiating elements and feed networks. So depending on the topology that you choose to implement LC technology. So as I mentioned, this is a phased array technology. There are, of course, other the companies using liquid crystal technology. This is simply the different topology. So we use the phased array. A lot of know-how is available. The question we ask ourselves is how to implement those things by using LC. And since 2017, we actually work hard how to use existing production line as it is. So we change our antenna design, we change our electronics design or panel designs so that existing production line can be used more than 80% as they are. The difference is basically the antennas are operating at, let's say, Ka band 30 gigahertz to 20 gigahertz. So the metal thickness is the only difference when I compare the TVs and the antennas. Other than this, actually, you can use everything, almost, let's say, like display people are using. So that was important to reduce the overall cost of the panel from our perspective. So last year, in the middle of COVID outbreak, the team worked hard. We achieved successful demonstrations together with the partners in industry. So we implemented a Ka band antenna, which has transmit and receive capabilities, and step by step, actually, we showed the antenna function as this. So now we can do continuous beam steering plus minus 50 degrees, which means we already, let's say, developed techniques how to calibrate the antenna. This is an inline calibration. This is an important topic for, I believe, any electronically steered antenna. So we have a very good concept for that. We achieved let's say the performances that customers are asking for. And just before last year, Christmas holidays, we made a live demo with two-way communication test while antenna was on the move. That means our antenna patterns, cross-polarization levels, and so on, that have been checked and approved by the satellite operators, and we did such a demo successfully with the industry partners. And we also show that the very low power consumption of our antenna concept. At the moment, we are working towards our LEO antenna, so you can see the specifications. It will operate at the commercial Ka band frequencies. The instantaneous bandwidth is around 400 megahertz. It says circularly polarized antennas, and G over T is around 10.8, and IRRP is 45 dB watt with 6 watt buck. We have a fully passive antenna, so the size of the antenna is around 55 by, let's say, 100 centimeters. This is an enterprise antenna, so we didn't optimize the thickness. So the thickness of antenna will be around 9 centimeters. But on the 5G program, which we are running in parallel, the antenna thickness is actually less than a centimeter. The power consumption of the antenna module is around 35 watts. And once we add all, let's say, once we talk about the terminal, including the LMB buck, so it will be less than 100 watts. And very important is the cost of this antenna will be 1,500 euros, and this is the cost of the antenna module. And we can achieve a 400 megabits per second, of course, depending on the satellite, the waveform, the bandwidth, but with the potential customers, we made analysis, and this is what we can achieve. So thank you very much again for having us here. I'm happy to get your questions.
Thank you, Onur. You mentioned that the instantaneous bandwidth of the antenna is 400 megahertz. Is this the perceived requirement, or is it a limitation of the design?
This is the requirement that we are getting from the customers. Of course, there are some customers who are also asking 500 megahertz, or maybe even sometimes around 800 megahertz. So that is actually liquid crystal phase shifters are true time delays with a limited, let's say, phase shift. So this is not pure true time delay, and this is also not pure phase shifter. So this is something in between. So you can increase this. That could be more than 400 megahertz for sure, but that's the specifications we fix for that antenna.
Okay, we have a question from the audience. What do you think about optical IF beamformers? Optical IF beamformers. I mean, as I'm actually technology-wise, I cannot say anything right now. I have to really deep dive into that one, but people who are asking this question, I think it's better to check the web pages and to see which markets that people are heading towards. So this should give an idea about the cost of the antenna, and I believe this is the main differentiator. As I mentioned, the antenna topic is not new. Last at least 2 decades, people have been working on that. We don't see really something really new, yeah? Just the trade-offs that people are deciding, and based on those trade-offs, you either pay from your performance or from the cost and so on. So
at least the optical beamformers which is available, which I can imagine at the moment, the main difference I see is the cost and the markets that we can address.
I'll take one last question, which is regarding the switching speed of the array and the temperature dependency of the LC.
Yes, liquid crystal, I mean, like actually any material, liquid crystal also has temperature dependency. Actually, by working Merck, I tried to address this at the beginning. Merck is developing micro-optimized liquid crystals, and the response time is actually one of the parameters. So we developed a lot, and we are already developing this LEO antenna together with a potential customer, MEO antenna. So there we will have only one antenna, and we have a slew time, for example, given in this data sheet, it is less than 20 milliseconds. Actually, with the new liquid crystals, now we are actually in the range of single-digit millisecond. So this is improving. Basically, this means, for example, if it is 10 milliseconds, during handover, you may lose your link around 10 milliseconds. I'm sure this is an issue for high-end customers like military, maybe for aviation, or also for some governmental applications. But for consumer markets, again, we did all those analyses together with our, let's say, potential customers. You can compensate several hundred milliseconds. So our antenna is quite fast and can achieve those targets.
Thank you very much, Onur. We move to the next presenter, Carl from Untitled. And the presentation is entitled A Service Provider's Perspective on Hybrid Service Provisioning. Carl,
Hey, Barry. Yeah, if Onur could just stop sharing his screen.
We can see you. That's good.
All right.
And we can see your screen as well.
Good. Thank you very much, Hector. I'm going to have a slightly different version of the previous presentations. I'm almost at the graveyard session, so maybe a slightly different perspective on it. And it's related to, service providers and our perspective on hybrid services. I'm Carl Kepke. I look after connectivity sales for Anuvu. Anuvu used to be known as Global Eagle. We went through a Chapter 11 process and also rebranded as Anuvu. We have new ownership, new financing, which is all good for us. We're very happy. We also very firmly believe that, as technology changes, we have to move with the technology, but it also comes with some associated issues as a service provider. I recall from my days in R&D that it's always nice to bring new technology to the market, but as a service provider, we have some challenges. Now, from a service provider point of view, we concentrate on mobility. So aviation connectivity and maritime connectivity, and then we have a business that looks after media and content. But obviously, I'm going to concentrate on the connectivity side of our business. I think what is important to the audience here is just what gives us the right to talk about this. So we as a service provider, we provide global services. We're running about 22 teleports globally. We're bringing up a couple of new ones this year as well. We have about 1,000 employees spread across the world. When we start looking at our aviation connectivity side, we have quite a lot of satellite capacity that we've assigned to it. And then if we look at our maritime solution, we actually, from the 22 teleports, access 54 satellites and provision over 20 gigabits worth of capacity globally to maritime and aviation connectivity clients. And I think it gives you a kind of a feel on the challenges that we would be facing. I mean, we look at KU, KA band systems. We have over 1,000 aircraft. We have about 66% of the maritime cruise ships that we service, we provide. We have over 1,000 vessels on the oceans. Multiple airline customers service a huge amount of passengers on these airlines and cruise ships. And obviously, when you start looking at new technologies, it always is a timing challenge, because once you've invested in a particular technology in a teleport and in a network, you start looking at the long-term provisioning of the service. And obviously, we got to look at satellite technologies, we got to look at the remote terminals, infrastructure build, and then support systems, because every time you bring in a new technology, you need to look at the support and the network management for that new technology. So when we look at aircraft terminals, you know, we started off with some of the newer systems where we had an aperture-based antenna, which we're still using. But as soon as you start putting equipment on an aircraft, you really require a whole bunch of regulatory certification. And it's connected to the communication side, so not just aviation regulations, but also telecommunication regulations, in that you need to meet regulatory requirements for separate countries across the world. And then on the aviation side, obviously, there's a very large component of safety and related to that. So, you know, when you start looking at bringing in a new piece of equipment on board an aircraft, you're looking at least 24 months for certification to bring in new technology on. So I really appreciate all the previous speakers about the new antennas and new systems they're bringing on board. But, you know, we absolutely welcome any new technology, because it makes it faster, cheaper, better. But we have to look at the phasing, and we have to look at how we bring it onto the network. We also very much in the aviation business dependent on the airline itself and aircraft and personnel availability. You know, to just quickly change an antenna on an aircraft is not a simple process. You need to ground the aircraft. A narrow body aircraft would cost about $40,000 to $50,000 a day to ground. A wide body aircraft is $150,000 a day. You need hangar space because you're obviously opening it up. So these are not simple processes, and I believe the ThinCom folk also have sympathy with us, because it is not a quick solution to just change antennas. And I thought what I'd do is kind of give you a step in the evolution of antennas. So this is an antenna. This is a 2-axis antenna that we've been using for many years already, very successfully, still flying on hundreds of aircraft. The next evolution is a 3-axis antenna, which has been flying for about 3.5 years. Very successful. We're very happy with the performance of it. The next evolution is a dual antenna, a dual aperture antenna that will start flying now. This has also been certified on the Telesat Lightspeed network. In actual fact, we've already tested it on board our own aircraft and successfully switched between a GEO satellite and a LEO satellite. And then obviously, when you start looking at the newer generation antennas, this is what we're looking at probably in the next 2 to 3 years from now. So I think I wanted to do this to show you kind of an evolution from a service provider, you know, how we go through antenna upgrades and newer technologies in the process. And then obviously on maritime solutions, we're not that constricted, because obviously we are able to get on vessels. We are able to look at different antennas, but we are starting to see electronically steered antennas, hybrid antennas coming into the market on maritime platforms. And then obviously we got the mechanically steered antennas, which are freely available on maritime platforms. But obviously, as we start looking at LEO constellations and MEO constellations, these antennas specifications have to start changing. But obviously, you know, we also got to look at the data rates and availabilities. When you look at network and support systems, it is not just the equipment. You got to look at the NOC support. You got to look at the field support, LOU support, line replaceable units. So, you know, how do you support the repair and maintenance of these devices on board aircraft and vessels? How do you stock it worldwide? And then the other thing that is kind of interesting is when you start looking at a network like we have, multi-link budgets, and I use that example because we got link budgets of vessels that sail in very low elevation regions. We have aircraft that fly all over the world. They all have different link budgets. We use, like I said, over 50 different satellites. Each one has its own characteristics. So when you start looking at the management and the satellite capacity management and the link budgets and managing an SLA on an aircraft, it becomes quite a tricky situation. And we're starting to deploy AI technologies and lots of data analytics to manage our network performance. And when you start looking at the satellite architectures, obviously there's a drive to higher throughputs, newer satellites. So we've actually just recently announced what we call the Anuvu constellation. We have signed up with a micro geo system where we are looking at Astranis, and we've actually signed up for 8 satellites. The first 2 will be deployed in the US Caribbean market. And the attraction for us with the micro geos is that they can be fairly easily configured. We don't have to change anything on the ground. We don't have to change anything on the terminals. It acts like a normal geo network, but it allows us to really concentrate capacity over a particular region, which in our situation is quite important. If you look at aviation customers, if they have particular hubs, if you, for instance, flying with Turkish Airlines, you know, they have a huge amount of aircraft landing and taking off out of Istanbul. So it's important to be able to layer the capacity over high density regions where your customers are flying or where they're utilizing the bandwidth. And in maritime customers, you know, obviously the Middle East, the Mediterranean and the Caribbean are high density regions that we need to look at. So like I said, you know, the first Astranis micro geos, 2 of them are going up over the US. We are looking at 6 more to deploy in the next few years. But we also have a very definite move towards a LEO constellation, and we're associating with Telesat Lightspeed, which will be coming online 2023-2024 timeline. And we believe that Telesat is a very good solution for us. The one thing I think differentiates it a little bit from the other LEO constellations is that they are geared towards enterprise type services. So they prepare to sign up for SLAs, jitter, and carrier grade services, which obviously in our environment is quite important. And, you know, so when you start looking at these LEO constellations and a hybrid of LEOs and GEOs, you need to start looking at how you're going to be provisioning it onto aircraft and ships. And on aircraft, obviously it's slightly less of an issue because you obviously already have an antenna that needs to do tracking of satellites. But it is something that we planning and we have a 2 to 3 year horizon with the launch of Lightspeed and operational capabilities coming in then. I'm not going to talk about Lightspeed. It's obviously 298 satellites, 2 different types of orbits. But we believe that it's kind of interesting because what it allows us to do is to be able to offer really high speed throughputs onto mobile platforms. We're looking at gigabit speeds into vessels. We're looking at hundreds of megabits onto aircraft. It also allows us to concentrate capacity, which obviously, as I mentioned, is important because we need to start looking at particular regions where we're offering services and we have an SLA requirement. And what I mean with high capacity regions, for instance, this is a maritime example, but in the Caribbean, we have a high concentration of customers that require services. So we are able to then deploy this capacity of Lightspeed in that region. In Europe, we obviously have the Mediterranean and the North Sea region. But likewise, on aviation customers, we need to be able to concentrate it over hubs of our airline customers. And we cannot work with an environment where you have a non-concentrated concentration of bandwidth. And it's important in a solution that we provide that the antennas and the ground segment equipment can support this type of activity. So Barry, I think I made my my time limit here. Just
very good.
Questions.
So there's a question from the audience. What orbiter slots will microgeo use over the US? reviewing coverage and look angles?
I am not at liberty to tell you what the orbital slot is, but it would be covering the whole continent of the US as well as the Caribbean. Okay. And obviously, when we start looking at aviation applications, we're very sensitive about the look angles so that we can support aviation customers.
So I have a question on the same constellation. What is the capacity of each satellite, and what is the frequency of operation, the bands that are used?
Okay, so the Astranis one is selectable between KU and KA. And then depending on what the application is in the link budget, so for aviation purposes, obviously the link budget is slightly less than, the throughput on the link budget is slightly less than for maritime customers. But on the aviation side, each satellite would be able to support up to about 8 gigabits. And for maritime customers, it's in the region of 20 gigabits.
Thank you. Thank you, Carl. I think we'll let you go. Not really let you go, because you
don't go away.
Thanks very much for the moment. And we'll move on to the next presenter, Ron from Milsat. Ron?
Don.
Sorry, Don.
Hello, everybody. Thank you for sticking around. I think I'm the bringing up the last of the presenters. Thank you for your patience and waiting for me to join in on the panel. I'm going to be talking about something completely different than what most of our presenters have been talking about. And man, what a lineup of technology. This has been a very interesting presentation. I want to thank all the presenters for talking about their technology. I'm representing Cassiopeia. I'm on the board of directors of Cassiopeia. Cassiopeia is a startup company, a joint venture between Oversat, ASAT, and Milsat. And it's a working towards a Bloomberg based antenna. There we go. So I must have jumped. There we go. So we're going to introduce Project Verizon antenna solution. This is based on the Lundberg lens phenomenon. It's sponsored currently by the Israeli-U.S. Binational Industrial Research and Development Foundation. The Bird Foundation has awarded Oversat and Milsat a joint effort, a $1 million grant to develop a Lundberg lens-based antenna. This antenna is, by its design criteria, being built to be operational on a OneWeb network. So it's a KU solution currently, but has the ability to be used on a variety of different frequencies. So this is a multi-beam, high gain, low cost, small, lightweight LEO terminal. Based on a Lundberg lens application, which is a unique approach to an old idea. I don't know if some of you may know what a Lundberg lens is. Historically, it's been used in a variety of radar applications. First, one of the biggest Lundberg lens that I'm aware of was on the HMS Victorious and its class sister ships, a 30-ton Lundberg lens, and it has evolved through the years to what we see today. A company called Loonwave uses it for autonomous vehicle radar applications. And one of the primary differences that you see in the technology is that the Loonwave application uses a 3D printed Lundberg lens versus a cast milled Lundberg lens. Lundberg lens, by its nature, is a multi-layer, much like a nesting doll architecture, where you have multiple layers, where the electromagnetic beam is amplified and bent towards a focal point on the back side of the Lundberg lens. And so using a method of 3D printing, we can reduce the cost of our Lundberg lens. The materials that go into the Lundberg lens cost about $15 in materials, compared to the millions of dollars probably that went into the HMS Victorious Lundberg lens manufacturing process. So for us, it is the manufacturing process of an old technology is the key to what we're talking about. We're embedding this Lundberg lens on a maritime stabilized platform manufactured currently by the Oversat group, which is part of the old Israeli orbit management and engineering group. 2013 started Oversat, so they have been successful in manufacturing a stabilized parabolic antenna solution. It's quite popular with a lot of different European navies and in Asia as well. And so we're going to embed this Lundberg lens, which is manufactured by ASAT, onto this Oversat stabilized platform, and using a combination of electromechanical and electronic beam steering, we will create a low-cost solution that has a high efficiency quota. Right now, we have an antenna in the lens currently in the chamber now, and we expect to be testing prototype live sometime in February. So we're very excited about that. I think I missed a slide here. I'm going to jump back here and talk just a little bit about Cassiopeia and who the companies are that are part of this. This is a brand new company. The BIRD grant was just released last week, and so we're just launching Cassiopeia. The ink's still wet on the corporate commission application as we move forward. But we're organized under Susan Snyder, the Chief Executive Officer, who's some of you may know as part of the old MTN organization, and of course Rear Admiral Yossi Levy from what was the Orbit organization, now Oversat. And so these three small companies are working on $1 million grant. And very excited about what this represents. This Lundberg lens can be shaped into obviously a sphere, which is where we are leveraging the horizon to horizon capability at the same efficiency as we would at zenith. Right now, this lens in the lab is running about 60% efficient. We expect to get that closer to 75 by the time we run the prototype. So this means small, lightweight compared to a parabolic in our application. We selected the maritime market because of all of the reasons that you heard about. The aeronautical community is a tough and expensive and time costly arena to introduce a new product. The maritime arena is enterprise environment market, and so I don't have to build 1 million of them to be profitable. I can build a few hundred and make a profit at the end of the year. And the maritime market is very receptive to new technology insertion. So we feel that our solution to the maritime market to start is a good place to go. The BIRD Grant Foundation puts this on a 2-year timeline to market, but we expect to have a version of this ready in about 12 months, ready to begin a manufacturing process. The factory is initially going to be set up in Israel. So the Lundberg lens can be shaped into a variety of different shapes. Does not have to be a sphere. It could be shaped into a loaf of bread or other forms to accommodate the installation environment or special applications or special beam shaping requirements. We see the future around this old technology, the Lundberg lens, opening the door for a variety of applications, which includes gateway antennas and the consumer level antenna. This, because of this, the low cost of manufacturing, we see this as really the technology that's going to lead the way to very, very low consumer cost antennas for satellite communications in a big way. So keep an eye on us. We're just getting started, but I think we're going to take this into areas that nobody really expects. So anybody have any questions?
Thank you, Don. I have a question. I see none from the audience, so it might be short. Using today's technology, if you were to reproduce the antenna on HMS Victorious, how much would it weigh?
Well, the HMS Victorious was running megawatts of power. A lot of the weight associated with that particular Lundberg lens was just plumbing used for coolant and pulling all of the heat away. That antenna wasn't necessarily that efficient, but it was the first multi-target tracking air search radar in the world. So it was highly advanced, but was running a lot of heat. So most of that weight, that 30 tons, was water or glycol for the cooling. The lens that we see now that you saw in the lab, that's a 30 centimeter lens. It weighs about 1.5 pounds. You know, just less than a kilo. So it's
700 grams. Say.
Yeah. So
okay.
Very lightweight. The lens that you saw from the Loon Wave is just a few ounces. That's as light as a snowflake.
Thank you very much. So right. We'll close the presentations there and we'll move to the panel discussion. I've prepared a few questions, 3, I think. And what I'd like to do is I'd like to hear what you have to say on each one of them. So the first one is that roughly today the market is split between KU and KA. We can extrapolate to other bands as well, but for the moment we'll stick to KU and KA. In 5 years' time, how would you see the split of the market? How would you see the market split between the 2 frequencies? And if you're really ambitious, you can go beyond in 10 years. I won't push anybody to talk first. I'll let the first speaker take the floor, whoever that may be.
Well, I'll get us started. I think of these frequency bands, you know, just as KU band came on after C band, and C band is still around, and I think it will continue to be around. KA band, I think some people had viewed was going to replace KU band, but I don't think that's really happened. My feeling right now is, as of today, I think there's enough NGSO constellations in each of the 2 bands. There's enough GSO constellations in each of the 2 bands that if you were to pick one, you're going to get full coverage. You're going to be able to work with 2 or more NGSO constellations. You're going to have not only what used to be just regional coverage at KA is now global coverage at KA. It's been that way for some time at KU, but we noticed that the KU satellite providers, they're certainly not yielding to HTS. I mean, they remind everyone that HTS is not a term that's reserved just for KA. So our feeling is that it's because there is generally some price, cost, weight disadvantage of carrying both bands. We suggest to customers they pick one band, and we think that's not a particularly dangerous solution right now. And then the last part, and then I'll tee it up to everyone else, is I mentioned I prognosticate that Q and V band are going to start to be used in the user terminals, just because that's 10 gigahertz of bandwidth that's really not used too much. It's already approved, so it's relatively straightforward to license. And we can't imagine that satellite providers and ground providers are going to let that stand unused for very long. Back to you.
Bill, for example, you've mentioned that you have over 1,500 antennas. What's the split between KU and KA, for example?
Sure. So of the 1550 that was on the charts, about 1,600 is KU, and then not shown there. In addition to that, we have about 300 systems installed on aircraft at KA.
So at the moment, you have more KA than KU.
No, more KU than KA,
more
but
KU. That's
KA
what I
catching
thought.
up. Right.
Okay. Because the way I see it, you mentioned that HTS systems are not specifically limited to KA, but one of the main reasons why HTS exists in KU is because of aviation. It's one of the driving markets, I would say.
Mm-hmm.
So if that market were to move to KA, then perhaps the reason for that market would decrease.
We'll have to see. I mean, the folks from Intelsat, in terms of, well, each group has their own sort of culture and decide, but I mean, Intelsat is certainly doing some exciting stuff with at KU band with HTS, VHTS, XTS, talking about spot beam sizes that are down to ½ a degree and smaller. So that's a lot of frequency reuse.
Yeah. Anybody else?
I expect the current split to stay the same for a while. The 75-25 split. Well, all the capacity that's coming online in the next 5 years will be predominated by KU in LEO space. So I wouldn't expect that split to change dramatically in the next, we'll call it at least 4 years before KA LEOs pop up.
I think what I'm seeing more is it depends whether you're looking for a global operation or a regional operation. And there's there's GX and there's Viasat 3 constellation, but a lot of the KA demand has come from consumer broadband, which is mainly focused around regional KA services, especially consumer. So on the enterprise side, I think you're right, it's going to be predominantly KU going forward, but there'll be a lot of regional KA providers providing very low cost consumer broadband services. I think that you'll see a lot of growth in that.
Okay, anybody else? Okay, we can move to the next question. If we were to split the market between commercial and governmental services or applications, how do you see the share evolving, the relative shares evolving over time?
Just quickly, from our perspective, we're seeing more interest, demand, and budget allocation to the government projects than the consumer or the commercial enterprise. A lot of the situation with COVID has taken a lot of the budget away for a lot of commercial stuff and pumped it into government type projects. So especially in the US, DoD, and some of the regional military projects, we're seeing an acceptance on taking on the antenna quicker, price being less of an issue. I don't know if that's going to stay. Obviously, it depends on where the demand for connected vehicle and other low-end consumer type services come, but definitely at the moment, government and military is a growth area.
Yeah, I have to agree with Rash. It's definitely headed government right now. There's a huge demand for new technologies in the flat panel array, both Chimetas and our antenna, and pretty much anybody that's got a new antenna, the government wants it. So as far down the road as we can look, I see it staying predominantly being government centric.
I think from our perspective, we see a lot of, not just from the antenna side, but also from the government business side, a lot of USO requirements, especially since governments are doubling in efforts and putting in more money to connect people internationally in underserved areas. So we just see a lot more money in government subsidies and initiatives across the globe.
Although I might add that on the government side, of course, and I think everyone would probably concur with this, the government really says that they're moving away from government, specific sovereign constellations, and that because they want to be able to exploit what's happening commercially in GEO and what's happening soon in LEO. Although I think it's going to be interesting, you know, when we have cyber, we're also talking about resiliency, cybersecurity, anti-jam, low probability of intercept, low probability of detection. I think it's going to be difficult for government users to rely solely on commercial constellations, and we'll have to see how that evolves.
The whole fighting Satcom technology that's coming out of the LA area is going to drive a lot of that, Bill. Once the government figures out that they have to be able to support our waveforms and we have to support their waveforms, then we'll start seeing a more ubiquitous overarching network. But they're never going to get away from their MilSats and their the WGS networks and all those.
Yeah, I agree with Bill and Russ. I think the military is going to drive a lot of this technology. Their demand for bandwidth is insatiable, and the requirement that's on the board right now is to push as much as they can onto a LEO type network for resiliency. There is a real concern at the Pentagon about bad actors destroying GEO and ground-based assets. So with the new capabilities of hypersonic missiles and space destruction weaponry, the answer to that in the short term is to push as much bandwidth being used by the government onto the LEOs, which is why you're seeing the LEO market in a boom right now. It's because of government money.
Just sorry to add one thing. I think the elephant in the room is actually how much of an influence and how much interest the telcos and cellcos play in this satellite world. Because potentially, if they start adopting flat panel antennas for USO or rural connectivity, every country, look at LATAM, look at Africa, look at, you know, some areas of Asia, they could be deploying hundreds of thousands of relatively low cost flat panel antennas for not just home connectivity, but SME SOHO connectivity, which is, you know, home office, as we've seen with COVID. So if they're willing to do subsidization of product, as we're seeing with like BT OneWeb type deals, that could be running into the untapped type of numbers.
Anybody else want to add anything? Okay, so we can move to the last question. Cost. Starlink have quoted their antennas costing $300 initially. It's down to 1,500 now. At least that's what they say. And they're charging people 500. How do you see the prices evolving over the next 5 or 10 years? Obviously, it could be in relative terms because it may not be important to have absolute numbers at this stage.
Well, cost to manufacture is going to evolve based on volume and demand, obviously. Starlink is giving away their antennas at a loss. I don't think any of us on this panel particularly want to intentionally give away money, but Elon has money, so he can. We just went through a huge exercise on cost to manufacture and volume, and we're rapidly coming to the conclusion, working with Plexus, that we can manufacture our antenna relatively cheaply compared to what we thought we could. So over time, the more people that want the antennas, whether it's ours or anybody else's on the panel, the prices are going to drive down. How far? That remains to be seen.
I think we shouldn't forget two things here, and I agree with Russ, what Russ said. You know, there was, in the old days, there's talk of KA band, HTS driving really low cost services for consumer, for example. But when you get the antenna, we shouldn't forget the additional cost that importation, homologation, all these other additions was drive up to $3,000-4,000. Someone has to subsidize that, and it's usually
certifications.
Right. And yeah, absolutely. And the other thing is that, you know, there's a lot of talk about driving the cost of the antenna, the ground system down. Let's not forget space segment. That's the recurring cost. And recurring cost is probably the biggest element for a network. If it's inefficient and you're paying large amounts every single month, a one-off cost is irrelevant to a certain extent, but you can amortize over 5 years. So we shouldn't forget, it always seems to come down to the cost of the antenna, but there's a cost of the space, which is very, very important as well.
Yes, but if you look at HTS systems, the space segment cost to the final user is more or less similar, of the same order as terrestrial services. It's the CPE that makes it significantly different.
True.
The terminal costs, say, $300. A modem that you get from, I don't know, the Vodafones or whoever the incumbent is, you get it for free practically.
But it requires the same model needs to be applied that the telcos are doing with the modems, with the mobile phones effectively. The same model has to be applied in the satellite world. Now that's possible with someone like a Amazon or a SpaceX. I'm not sure it's going to go across the whole satellite world at this stage.
Okay, there is a question from the audience. The NGSO sky is looking increasingly cluttered, and despite everything, I fear there will be real inter-system interference unless off-axis performance is at least as good as it is with conventional geo antennas. Do suppliers of antenna based on non-parabolic technology agree with this fear? And if so, what is their thinking regarding this? And with the goal of having enough satellites, is enough constellation in enough constellation to ensure proper competition as there is in geo. So basically, off-axis performance and inter-system and intra-system interference.
Well, if I could, because I touched upon that a little bit in my presentation, it wasn't that long ago, only a few years ago, that we really were concerned only with what's happening within plus or minus 2 degrees, plus or minus 4 degrees, plus or minus 6 degrees, meaning adjacent satellites in a GSO plane. But quickly now that's changed. And with NGSOs, with GSO licensing, we always talked about NGSOs and even provision for it. Maybe sometimes we'd ask for a waiver for off axis out of the GSO plane with the pledge that we'll coordinate if and when NGSOs ever come up. Well, guess what? They're here. So this now these bets are being called in. And so what is becoming important is the GSO plane is just part of the problem. The issue is when you're operating on an NGSO, and a GSO may have primary privileges in that particular band, it's your responsibility as the NGSO terminal to protect the GSO plane. Even when you're pointing to the north, in the northern hemisphere at an NGSO, you need to make sure your southern oriented side lobes are very low, because that's where the GSO plane is. And as I mentioned, in terrestrial users, this is coming up, I think, a lot on gateway systems that have to work at low elevation angles. The terrestrial folks are also using these same bands, and this can be a really big deal. There's people even taking their gateway systems, I understand, and burying them. I mean, putting them in making a recessed area to use the Earth itself to help shield terrestrial to meet those requirements. And then the responsibility, and I'll just bring up like Starlink and OneWeb, which I think is going to probably be the first thing we hear about, is OneWeb, I believe, I don't know in stock in the company, has primary privileges in KU band NGSO over Starlink. So that means that Starlink needs to make sure that, some radius, some diameter, maybe 8 degrees, 10 degrees around every OneWeb satellite as it moves, it has to make sure its terminal is not broadcasting within that circle. It also has to make sure, Starlink has to make sure they don't broadcast within about 12 degrees of the GSO plane. So the management of this in terms of where you can point, when you can use this band, when you can use that other band, it's going to be very, very complicated. And I just think in terms of momentum, we're way too slow. I think we're driving a little ahead of our headlights, if you will. And I think we're going to find out about problems with interference, and it won't be too late, but the momentum will be going forward it may become a big problem that will be difficult to solve.
I think, well, I know that what you said is correct, Bill, because in these bands, new systems have to coordinate with old systems. And therefore, since NGSOs are newer than GSOs, they have to coordinate with GSOs, and the new NGSOs will have to coordinate with all those. So it will become increasingly difficult for newcomers.
Agreed. It'll be interesting to see how the ITU, the FCC collaborate to do that, to moderate this.
The ITU has designed the system, the coordination system, based on 2.5 constellation systems, whatever 2.5 means. We already have about 4 or 5 of them. So probably the interference level is beyond what they have imagined.
Right.
Which does all kind of suggest that the questioner is valid in his concern. I think if you go back to the period of just trying to get parabolic antennas working with geostationary antennas, the qualification process on that was itself fraught with each geostationary satellite operator pretty much having its own standards. And there was the hiatus of people doing approved antennas and type approval processes, which cost fortune. And then having insisted on some of the high-end manufacturers doing it, the satellite operators, because they offered revenue, accepted any old dustbin lid to come onto the service. And the noise floors on all these spectra now are at least 3 dB higher than they were in the early days. So we were completely unable to manage the parabolic geostationary system. And as you say, at this level, when you're now getting into the multi-orbit and satellites all over the place, then I think it is a huge risk and a huge challenge. But I think fundamentally, if you have got a very clean main beam and you have very low side lobes, then obviously you're in a much better position to address it. And I think the manufacturers are in a very difficult knife edge of, you can get better beams with a full element array than you can with a parabolic dish, because you haven't got indentations and interference from subreflector supports and such like, and mispointing errors. So you can get very good performance from a full element array, but it has cost implications, and some of the lower cost possibilities for antennas probably do, in general, compromise the off-axis gain performance. So there's a commercial angle on it as well. So yeah, it is certainly a problem, and not being addressed very carefully. I think it is just too complicated. So it's being put in the pending file.
But the part that causes me most concern is not just the fact that this problem exists, but it's the wide range of understanding that the various NGSO operators have to solving, or at least identifying, the problem. So some fully understand it and are working to fix it. Some don't know it's a problem yet.
Yeah.
So
I've
we're getting a bit late. Okay,
I've got a question. Now, to the electronically scanned array user terminal people, this is a question concerning the Asic silicon chips or the equivalent. So what is the current status? Are they improving in performance? And is there lower dissipation? The prices seem to be too high, and the availability is a little bit strained at the moment. And just as a comment, 2-3 days ago, listening to Bloomberg TV in the morning, I did hear them say that there's been a 300% increase over the last year in silicon chips. How's that going to affect you guys?
Is that 300% increase in demand or 300% increase in availability?
In the cost.
Yes, it absolutely is affecting us. Your first question was, how are we increasing in availability? Not availability, in usability. Basically, every generation gets better. That's kind of the point of the exercise.
Is yield the word you're looking for? Yield?
Yield. That's the word I'm looking for. Thank you. It's still pretty early on this side of the pond, guys. The idea that, no offense, Bill, I know you're pushing it too. The more people are demanding chips, the prices are going to go down, whether they're chips for my antenna or chips for David's antenna or chips for Rash's antenna. It doesn't matter. The price is going to go down because people are going to requesting them. Problem is we're being throttled by the manufacturers to drive prices up. We can make all the requests they want, and they say, well, you have to pay more for them. So there's the long-term problem that we all have to face, and that's global markets and who controls what. So that's the response from this side. Anybody else want to chime in on that one?
I can take part of it. I mean, Barry, I think the question really revolves around the supply of chips. And, you know, at Nexcom, we made big bets on the chips that we picked and bought a lot of them. So we have a contracted price for a given amount that helps drive us in the markets that we're satisfying. And, you know, we got plenty of supply.
Good.
You know,
that's good buying ahead. That's good thinking, good strategy. Yeah.
Okay, so if there are no further comments, perhaps we'll get to the closing remarks, where I'd like to thank all the participants for their very interesting presentations, ranging from new technology to old ideas with new technology, new concepts, and even system level enhancements. I found the presentations very interesting. And I'd like to thank you again for your participation. There's a question from the audience whether the deck of presentation would be available. I don't know what's the situation. Perhaps Daphne or Barry knows what we normally do, whether they're available for distribution.
Yes, they will be available, and I'm sure it will probably be available tomorrow. But Daphne, she is the contact point, and she will be able to appraise you of what's happening.
I will be getting everybody's official approval, and then I'll be sharing it.
Oh, okay, yes, all right, okay, yeah.
So Daphne, I presume that you'll be needing the final approved version from all presenters.
Exactly, yeah.
Okay. Okay, so
I've got to say my few words now.
I just say goodbye and thanks very much, and then Barry can say what he has to say.
All right. So, hey guys, I think it's been very impressive. It really has. If I had to give a best paper award decision, I am going to have great difficulty in making that decision. It was marvelous. Well, I'd say to our audience, follow these acts. And I mean, from point of view, I know this is a virtual thing, but it's been really impressive. And we've had a comprehensive coverage of what is relevant when it comes to modern ground station user and gateway terminals. And for now and the next 5 years. So this is going into the future. So here I need to thank the following persons. So Daphne, Lael, and Jim at Profen, our main sponsor. Our sponsors appreciate support Profen, Hughes Network Systems, and Anuvu. To all presenters, and that's you guys there, great contributions and great stories, without which today would not happen. Then turning to our wonderful moderator, that's you, Hector. Thank you very much for participating, and we give you special thanks. Now to you, the audience, thanks for staying the course. It's been a long time in this. We trust you have benefited. I think I have immensely. Finally, my personal summary. We've highlighted many technical and commercial KU, KA, and even W band operational solutions for consumer, enterprise, and high-end applications. Summarizing, The conventional FPA array from Profen. Thank you, Hakan. Great. Use of the novel spherical reflector antenna from Freefall. Douglas, thank you. The multi-beam FPA electronically controlled pointing and polarization mechanism using metamaterials from Kymeta. Thank you, Raj. Multi-beam ESA phased array technology from Hanoi Phaser, exhibiting their first application with high-end yachts. Russell, thank you very much indeed. Multi-beam phased array for Aero and connected car and electronically steered gateway systems from Celestria. David, do appreciate your inputs. Multi-beam phased array electronically steered from ThingCom. Bill, great, all the way from Hawthorne. Flat plate electronically scanned antenna technology exploiting novel fragmented aperture elements by NXTcom. Glad you explained it all. And Steve, thank you very much. That's appreciated. Flat panel phased array technology features using latest liquid crystal technology by Alcan. Honor, great. Thank you very much. And not finally, but novel use of Lunenburg lens technology featuring market target tracking from Milsat. So brilliant. There was a lot of other things that I was going to go through, but I think time is of the essence now. Anyway, this is the start of something great, something good. And have we learned what the customer market expects, as there are challenges and potential roadblocks ahead? Definitely. For the new Satcom market as a whole, do we expect a viable and fruitful business future where cooperations with telcos is key, leading to this renaissance in Satcom, not now, but 2-3 years' time, when everything started to get up and running? Clearly establish what the customer wants from their digital connectivity. Additional and broader use cases as we proceed. Is low latency the big seller? These via these small aperture ESAs. Is there demand where no fiber exists, or is the demand where fiber is installed? Is it true the lower the price of the user terminal, the bigger the market? So reducing the cost of these terminals, the greater the opportunity for everyone involved. Clearly, constellation operators need to grow the size of their market pie. There was a chap from SpaceX, Hoffeller, and he's saying that 90% of IFC will be on LEO satellites rather than MEO-GEO for aviation and military markets within the next 10 years. Is that true? I mean, okay. Another thing is, of course, signal landing rights are key. Nobody's said anything about that and regulatory side too much. You may possess the greatest technology. If not accepted by a given country and region, then all talk becomes rather academic. And I mean, Turkey is sensitive to that. So still many challenges ahead there. Finally, I'm wrapping up now. Doing things right. A promise Satcom renaissance is coming, but when? Satellite will play an increasingly significant role in the greater telco business regime. personally, my 50 years in this business is mostly full of excitement, but wished somehow to be born a few years later to more coincide with the fast-moving, digitally connected age. So long live Geo, long live Meo, long live Leo. We wish you all well, and that's it for the moment, folks. So next year, hopefully, preferably face-to-face, and that would be far more interactive. So as we say, all of these are recorded and they can be retrieved from Daphne once she's done her assessment of with yeses. So that's it, guys. Thank you for getting up so early in some of these places, particularly California. I mean, it's really quite demanding, and it was good of you to do that. So thank you, and we're going to sign off then. Is that all right, Hector? Yeah,
that's great.
Okay.
Thank you very much. Bye-bye.
Thank you, Barry. That was great.
Thank you. Bye.
Thank you. Bye.